Hey team, Sid here with DevOps Directive, and welcome to this complete GitHub Actions course. I've spent the past few months building out what I believe to be the best resource for learning to use GitHub Actions effectively, and I'm excited to release it to the world. This course is for software engineers and DevOps practitioners who want to level up their ability to leverage GitHub Actions within their teams and organizations. Over the next 3.5 hours, I'm going to cover everything you need to know about GitHub Actions, starting with a solid foundation of platform capabilities, establishing the skills required to author automation workflows to meet the needs of your teams, and wrapping up by utilizing all of the skills and knowledge from the course to build a robust DevOps system based on GitHub Actions, containing workflows for building, testing, and deploying applications. While you're probably watching this video on YouTube, the video is just one component of the course. There's also a companion GitHub repo containing all of the code and workflows so you can follow along. Each lesson has a written module that you can see over at courses.devopsdirective.com, and there's a Discord community where you can join to interact with other community members if anything isn't clear or you get stuck along the way. Thanks to my sponsor Namespace, I'm able to provide this content to you free of charge. That being said, if you end up getting value from the course, you can help show your support by liking the video and sharing it on Twitter, LinkedIn, or within your company. Throughout the course, I'll go back and forth between theory sections where I'm covering all the different features that you need to know about and explaining how to use them, and then practice where we'll jump into the code editor, view, author, and edit workflows and actions, and run them both locally and remotely on GitHub to solidify your understanding of the various concepts. As I mentioned, this course is for any software engineer or DevOps practitioner who wants to level up their ability to use GitHub Actions. This could be because your current CI pipelines are taking too long and you want to understand how to effectively use caching, parallelism, or higher performance runners to speed that up. It might mean you're starting some new projects and want to do so in the right way with automated workflows built in from the start. Or you may have inherited a mess of YAML from a previous engineer and you want to learn how to understand and refactor it into a modular maintainable system. Throughout the course, we'll learn the skills to do any of these things and how to use GitHub Actions most effectively throughout your organization. There are some prerequisites for this course. First, I'm expecting you to at least have a base level understanding of Git and GitHub. Things like how to clone a repo, how to create branches, commit those, create PRs from those branches. I'm also assuming that you have a general idea of how to interact with a Linux shell or terminal, as well as writing and editing YAML files, which is the format that GitHub Actions workflows are authored in. I'm expecting you to have at least some coding ability in one or more languages. This could be JavaScript, TypeScript, Go, Python, but the ability to read and write code is somewhat necessary. And then finally, an optional prerequisite around Docker and containers. There is the ability to create containerized actions. And so for that, having an understanding of how Docker works will be helpful. I also have a comprehensive course on Docker and containers that you could check out if you wanted to brush up on those skills. Before we dive into the course content, I do want to pause for a minute and thank the sponsor of this course, Namespace. It's only through their generous support that I'm able to provide this course to you completely free of charge. I'm excited about them as a sponsor because I want everyone using GitHub Actions to know about them. Their products enhance the GitHub Actions user experience and enable teams to build, test, and ship software faster. Modifying just a single line in your configuration files enables you to use Namespace hosted runners, which can speed up your workflows while reducing costs significantly, but that's just the start. They also offer blazingly fast caching, remote Docker builders for speedups when building container images, and best-in-class observability with access to things like job timing and resource utilization, not available in GitHub directly. While using Namespace is not required to get the most out of the course, I will be showcasing where and how to use Namespace tools to improve your experience when working with GitHub Actions. If you want to get started with Namespace, there's a link in the description that you can follow. Full disclosure, this link is an affiliate link, so I will get some payment if you end up using Namespace. Because of this, if you do use them, I would appreciate if you use the link and let them know that you learned about them from me. So what are we going to cover in the course? We'll start by providing some context in terms of what GitHub Actions is, where it falls within the landscape of continuous integration tools, before covering all of the platform features that you're going to know about, from the basic core features to the more advanced features, as well as how to utilize the third-party public marketplace action, which is one of the big selling features of GitHub Actions, before authoring some actions of our own to use within our workflows. We'll then move on to how to engineer workflows that are going to meet the needs of your organization by examining some of the common workflow types, how to improve the developer experience when working with GitHub Actions, as well as best practices that you can apply to your teams and organizations to make your experience as good as possible. Finally, we're going to tie all of this together in an end-to-end Capstone project where we'll implement 6 different workflows that include testing, building, deploying a microservice-based application, all using GitHub Actions. And now, with those logistics out of the way, we can go ahead and dive right into the course. In order to provide historical context on why a tool like GitHub Action exists in the first place, it's useful to take a look back through the history of software development and understand why continuous integration is a thing and where GitHub Actions fits within the landscape. At the very early days of computing, things were done via physical punch cards. You would encode your program into a piece of paper with holes punched in it, and then those would be fed into a machine that would perform the desired calculations and output some result. This process took quite a long time, and generally, the people writing and producing the software were the same ones consuming it. These were executed on big mainframe systems. There was no notion of personal computing, so you weren't really delivering software out to an end user. You were writing the software for your own needs, executing it, and because of the amount of effort to author and generate these punch cards, the time between updates was generally very, very slow. The delivery mechanism moved from these physical punch cards onto things like floppy disks or compact disks or eventually DVDs. These devices could be written to digitally, and then you could ship, usually via snail mail, this device to an end user who would install it in their machine. Because this required shipping a physical device via snail mail, the time between updates was still quite slow, on the order of months probably, and the cost to ship an update was quite high. Continuing forward in time to the 2000s and the dot-com boom, we started to see websites and the internet take hold and software be delivered via the internet. So rather than needing to physically ship something to an end user, you could deliver a website or web app to the end user immediately over the internet. And this enabled a much quicker turnaround for shipping software updates. Now, in conjunction with this, because we're now able to ship updates much more quickly, the importance of the ability to automatically test updates before they ship became higher and higher. Now we move into the 2010s and into the 2020s, where we are today. And the highest performing software teams are shipping updates multiple times per day. Because of this, the tooling for building out and automating tests has continued to evolve. And that's where continuous integration tools like GitHub Actions really start to shine and become critical for these teams to ship quickly and safely. For those who are writing software today, the idea of continuous integration and automated testing may seem like table stakes, but before the year 2000, this was a totally novel idea. Companies were obviously building and testing their software, but this was often performed in a manual fashion on end user machines, rather than testing every single change automatically as it makes its way into version control. Looking way back to 1997, one of the first examples of continuous integration tooling came into play out of Netscape, eventually into Mozilla, and that was Tinderbox. And so this was a tool which would automatically look at their version control, and for each new commit, it would attempt to build the software for all the different platforms that they were going to deploy to, and then it would report the status of those builds back via this web interface. And this was a pretty revolutionary idea, and it enabled those teams to see if there was a regression introduced and one of the builds failed, to identify the bug and then fix that much more quickly. A few years later, in 2001, cruise control came onto the scene that was written in and primarily used by teams building software using Java. Similar idea, the ability to build your software and execute your test suites against them came out of a company called ThoughtWorks. A handful of years later, in 2005, Hudson was introduced. Hudson came out of Sun Microsystems, eventually acquired by Oracle, and it provided kind of a more user-friendly user interface and a very large plugin ecosystem that enabled you to handle a variety of use cases via those plugins. Eventually, it was forked and kind of lived on in the form of Jenkins due to some copyright issues with Oracle and the community wanting a more open version of the software. Some other key players in the space like Atlassian and JetBrains introduced their own continuous integration tools around 2006, 2007. And the interesting thing about these is that they had strong integrations with their existing product suites. So Atlassian was able to build Bamboo and have tight integrations with their tools like Jira and Bitbucket, whereas TeamCity was able to provide integration with their suite of IDEs, or integrated development environments, that they specialize in. If we move forward to 2010, we start to see some more familiar names come onto the scene, like Travis CI and Circle CI. Now, with these new entrants to the market, these were some of the first software as a service model continuous integration providers, where the company is generally hosting your runners and executing those builds as part of a cloud SaaS. And these really push forward the developer experience and the user experience of making it easy to integrate a CI tool with your version control and set up automated builds. Now, on the top there, we start to see entrants from the major version control platforms come into play. First, GitLab with their CI/CD product, and then eventually in 2018 with GitHub Actions. I'll talk about some of the reasons you might choose these different tools relative to each other, but when a version control platform releases a tool like this, they're able to have deep integration hooks with the rest of their platform, which can make it quite nice if your code is already hosted there. 2016 with AWS Code Build, that was the first sort of entrant from a hyperscaler cloud. GCP and Azure have their own CI tooling that was introduced not long thereafter. It can be useful if you're building and deploying your software all within one of those hyperscalers, and you want to keep your builds and test infrastructure there as well. This just provides a timeline, some of the key entrants in the history of continuous integration. As you can see, GitHub Actions was kind of a late entrant. However, because it is tied to GitHub, and that is the de facto standard where most teams are hosting their version control, it has a super low barrier to entry to getting started with. There's even an allocation of free build minutes that are provided for open source repos. So because it is so easy to get started, they've really ramped up quickly and become one of the more dominant players in the space. And now let's think a little bit about the types of workflows that people are running within these continuous integration tools. There's 4 main categories that I think of. The first is sort of validating things about your code and the changes to your code. So this is things like linting to make sure that your code is all formatted correctly and there's no type errors, etc. This is things like testing, whether it's unit testing or integration testing or end-to-end testing. Things like static analysis, of which linting is a specific type, but looking at security issues with your code, either in dependencies or in how it's written, or code quality metrics. So these type of validation checks are very common. The second category would be building your software. So for a compiled language, this would be building the executable itself. For other languages, this might be taking your software, downloading all the dependencies and bundling those into some deployable artifact like a container image. The third category then would be to take those deployable artifacts, either the binary or the container or some virtual machine image, and deploying those into a server somewhere. That could be in the cloud, that could be on premises. There's 2 main categories of deployment workflows, I would say. The first is push-based, so from within a workflow, authenticating to that server or that Kubernetes cluster or whatever the deployment target is, and issuing a command to push that deploy from the workflow. The other one that has become more common recently is a GitOps model where you have some agent running inside of your deployment target that is looking back at the version control and pulling in updates automatically. I'll talk more about how these work later on in the course. And then the fourth is sort of a broad category of repo automation. So because GitHub Actions has the ability to respond to lots of different types of events in GitHub, you can have things that are outside of traditional continuous integration to automate facets of your repositories, things like automating the release process based on commit messages, checking for issues or pull requests that are stale and closing those automatically, or things like finding potential dependency updates and executing those or creating PRs for those. All sorts of different automations that you could apply to your repositories. Now that we understand the context of GitHub Actions and the history of continuous integration systems, let's talk a little bit about why you might choose GitHub Actions over some of the alternatives. I found 2 industry surveys that ask many different developers which type of CI/CD pipeline tooling they are using. One was from the CNCF, the Cloud Native Compute Foundation, their annual survey, and one from JetBrains, so the IDE development company. And both of these ask a very similar question. What type of CI tooling or pipeline are you currently using? As we can see from the CNCF survey, GitHub Actions is the most popular option. We also see some tooling like Argo and Flux there that are really focused on only the GitOps or CD portion, so we kind of eliminate those. And so we look at the top few, it's GitHub Actions, Jenkins, GitLab, and then Azure Pipelines, which is quite similar to GitHub Actions. In fact, the GitHub Actions runner codebase is a fork of the Azure Pipelines runner back when they initially launched. Over on the JetBrains survey side, you can see Jenkins is in that top spot, followed by GitHub Actions and then GitLab. If we think about why Jenkins might be in the top spot there versus in the CNCF one, CNCF is going to be almost entirely companies and developers who have adopted Kubernetes and therefore are likely to adopt more recent or modern tooling. And so that's why I think GitHub Actions shines there, versus if you take the broader set of software developers, many of them may be at larger, more enterprise companies with legacy installs of Jenkins, which has been around for a lot longer, is much more common in some of those large enterprise settings, and is operating projects that have been around for quite some time, perhaps even longer than GitHub Actions itself. Here I've mapped out a table kind of comparing these top handful of tools. So GitHub Actions, GitLab CI/CD, and Jenkins were the 3 that we saw at the top of those surveys. And then I also included Circle CI as a CI provider not linked to a particular version control platform, but is able to link into many of those platforms and provides a bit of contrast to Jenkins, which is usually self-hosted, whereas Circle CI, they're generally hosting the runners for you. As I mentioned earlier, one of the big reasons that people get started with GitHub Actions is because their code is already on GitHub. There's minimal barrier to entry. You just add a YAML file to your repo. And this low friction means people start there and often end up staying there. There's also an expansive public marketplace, so people can publish their own actions, which are steps within your pipelines that you're going to execute. For many different common continuous integration tasks, you can find a public action that performs what you need to do and avoid having to write and maintain that code yourself. And then another reason why people choose GitHub Actions is because they are a market leader, it leads to improved tooling. There are many companies building on top of GitHub Actions, just like the sponsor of this course, Namespace, to build faster runners, better user experiences. And so that improved tooling is kind of a positive feedback loop where it's a better experience, which leads to more adoption, and so on and so forth. Some reasons you might not choose GitHub Actions is if your code is living elsewhere, if it's in GitLab or Bitbucket or some other version control system. GitHub Actions has less powerful expressiveness than some of these other systems. It's a simplistic syntax, but it does mean that in certain cases, you end up copying and pasting rather than being able to compose pipelines in a reusable fashion. We'll look at how to write and debug actions, but out of the box, the debugging experience can be somewhat painful, and also the default observability and analytics for GitHub Actions is quite limited. There's tools to help improve this, and using a provider like Namespace will give you some better observability, but out of the box, it can be quite limited. GitLab is an obvious contrast to GitHub Actions. Similarly, it is tied to the version control platform. And so if your code is on GitLab, you're likely going to choose GitLab CI. Again, if you are in that ecosystem, it's a minimal barrier to entry, has deep integration with all the other GitLab features. And GitLab has an interesting approach of auto DevOps, allows you to bootstrap an end-to-end CI system. If you're in a common language ecosystem, that they have added this type of capability for. Negatives for GitLab is if you are not using GitLab, you cannot use GitLab CI/CD, and also their marketplace features, so their ability to share and consume third-party capabilities is significantly smaller than GitHub Actions, whereas there's less than 500 total actions in that marketplace, whereas GitHub Actions has thousands and thousands. The quality of the actions in the GitHub Action marketplace varies wildly, but because there are so many more, the likelihood that you'll find a high-quality action that does meet your need is much higher. For Circle CI, if your code is not in one of those two major providers, but you still want a sort of cloud-hosted CI system, Circle CI might be a really nice option. There is a feature that they have built in called retry with SSH, that when a step in your pipeline fails, you can actually retry that workload and get instant access to the environment where that pipeline is running, which allows you to poke around and debug. There are ways to achieve this on GitHub Actions and other platforms, but having used Circle CI in the past, that feature is one that I miss when using some of these other platforms. It does require some additional initial setup. It's not tied directly into the version control platform like these first two. And also, like GitLab, its public marketplace for orbs is what they call kind of the reusable unit, is larger than GitLab, but it's still significantly smaller than GitHub Actions. Now, the fourth one here, Jenkins, as I mentioned in the history section, has been around for much, much longer than any of these other tools. There's kind of two positives for it, I would say. The first reason I can think of that someone would use Jenkins is that it is already set up and running and they don't want to invest to switch off of it. So there is some switching costs to rewriting pipelines and moving things elsewhere. And so oftentimes, if you have an existing setup and it works, if it works, there's no reason to break it. The plugin ecosystem is quite vast. So there's a number of capabilities that you can achieve within Jenkins by using those third-party plugins, kind of similar to the GitHub Actions marketplace. There's a lot of capabilities that have been built up over the lifetime of that tool. Some negatives, or why might you not want to use Jenkins, is that it is generally known for having quite a high maintenance overhead. Sort of keeping up with plugins as they are updated or have security issues can be a significant piece of work. And also the authorship of the pipelines, writing them is a language called Groovy, that isn't really used much elsewhere outside of the Jenkins ecosystem. And it can feel kind of quite outdated relative to the YAML structure that you may be familiar with if you're using these other tools. Now, before we start examining and authoring and running GitHub Action workflows, I want to pause and make sure we set up your development environment appropriately so that you have all the tooling that you need to follow along with the steps that I'm performing, and ideally minimize the number of snags that you hit along the way. Now, the first step that you're going to want to do is to fork the repo and then clone it to your local system, including the submodules. Now, the reason that we fork it here is because that way you can be the owner of the repo on GitHub, which will enable you to execute the workflows as you look at them, modify them, and then you'll want to run them within your own forked copy of the repository. This is the repo for the course. It's at github.com/sidpalace, DevOps Directive GitHub Actions course. To do that, you'll navigate to the repository. You'll go over here to the fork button. And while you're here, you may as well give it a star. But you'll click the fork button, You'll give it a name, choose which account or organization you should make it a part of, and then you'll click Create Fork. Once you've done that, you can scroll down in the README and find this git clone command and just modify this to reference your forked copy rather than the repo under my name. Because we've included recurse submodules, we'll get the Capstone repo as well. Eventually, when we start working on that, you may want to fork it as well, but for now, pulling in my copy should be just fine. Next, we'll install a tool called DevBox, which gives us a reproducible shell environment with all the tooling that I use throughout the course pinned to the exact version that I'm using, so you shouldn't hit any version dependency issues. The best way to do this is to go to their documentation, choose the system that you are running on. So in my case, I'm on macOS, and I can run this script to install it. Hey, Sid from the future here. As I was editing this, I realized I didn't mention this, but if you are on Windows, you should be using WSL such that you're executing these from within Linux. I haven't tested any of this on Windows directly, and so you'll have a much better time if you work within a Linux environment under WSL. macOS is the system that I use to develop and test all this. And then because we're using DevBox, which leverages Nix under the hood, package manager, hopefully things will work seamlessly across macOS, WSL on Windows, or Linux directly. All right, back to the video. Once it's installed, there is a devbox.json at the top level of the repo, as well as a devbox.lock file. These are what tells DevBox which tools to install. You can see all these tools that I'm using. I'm specifying latest here. I'm using latest at the time of recording. But by using this lock file, you will get the exact version that I have installed on your system. The nice thing about DevBox is it gives you this environment isolated from anything else on your laptop, such that when you're working on the course, you can have these versions pinned to my exact versions. But if you're working on something else, it won't pollute those installs elsewhere. Once you have DevBox installed, you can just run devbox shell, and it will look at your current environment, download and install any tooling that is not there, and start a shell session with all these tools installed and configured accordingly. Then we'll install Docker Desktop, which is useful as we get into some of the containerized aspects of building container-based actions and or using the tool Act, which allows us to run GitHub Actions workflows locally within containers. So having Docker installed is useful for that. For Docker Desktop, follow the latest install instructions from their documentation, choose the platform that you're on, and follow the instructions there. And then finally, I'm going to be using VS Code throughout the course. You could use other editors, but these are two extensions within VS Code that I found helpful for working with GitHub Actions specifically. The first one is YAML. This will give you YAML syntax, highlighting, as well as linting capabilities. And the second one is the GitHub Actions VS Code extension. So if we go into VS Code and you go under Code, Settings, Extensions, now you can search here for GitHub Actions. You can install that there. This is the official one. There's this other one here as well. I'm using the official one. It does provide a few nice things around actually viewing the actions that have run in your repositories from within VS Code. I don't use them that much, but it's nice to have installed. And then the second one is the YAML extension here from Red Hat. Go ahead and install that. One thing I did notice though, when I set both of these up, the GitHub Actions extension actually sort of takes ownership of any YAML file in those specific subdirectories, such that the YAML extension was no longer recognizing them as the YAML type. And so I added this to my settings, files.associations, such that any YAML file in that .github/workflows directory will be still associated with the YAML extension. And then similarly, task files were not being recognized as YAML. And task is a tool we use throughout the course for storing and running specific little shell commands and scripts. And so by adding it to this settings.json, now the YAML linting and auto formatting worked again. You can set these from within the GUI if you don't want to use the settings.json file by going under Code, Settings, Settings, and then searching Association. And you can see here for my user, I have files matching those two patterns associated with the YAML file type, such that the extension can do its job appropriately. Okay, the time has come for us to actually take a look at and write and run some GitHub Action workflows. This next module is going to focus on some of the core features, and then the following module will look at some of the more advanced features. This will get you up and running with the basics of what you'll need to run within GitHub Actions. And then throughout the rest of the course, we'll start to learn how to use these tools more effectively and design workflows that are really going to help your team execute at a high velocity. Before we actually look at the YAML configurations though, let's talk about some of the terminology so that we're all on the same page in terms of the different concepts you need to know and how we refer to them. On the left-hand side are GitHub events. So these are things like pushing to a branch in GitHub, creating a pull request, Any event that happens via the GitHub API or that you could have access via the GitHub API, generally you can see and respond to from GitHub Actions. These are going to trigger what is called a workflow. And so a workflow is what they call pipelines in GitHub Actions. So the thing that you are authoring, your file represents a workflow. Within that workflow, there will be one or more jobs. Each of those jobs can have one or more steps within them, and they can be ordered in a specific manner, as you can see here from this graph. And finally, the runner is the actual server environment that is going to execute those jobs. So between steps, you're in the same compute environment. Across jobs, you're in a different compute environment. So you need to think about that in terms of passing data or sharing environment variables or state between these different elements. Here's essentially the most simple workflow you can author. It's only 10 lines, including a couple of blank lines. We can see those concepts from the previous slide mapped onto it. So in the on section there on line 3, we've got a GitHub event. In this case, we're using the workflow dispatch event. That just means it's a manual trigger, so we can go into the GitHub UI and click trigger. We'll talk more about how to use the different events. For example, we could have a push event for when it pushes to a specific branch, or a pull request event for when we create a pull request. For now, we're just going to use that workflow dispatch in many cases so that we can manually trigger and see these things executing. Based on the outlined colors of those boxes, you can see the workflow is the entire thing. Jobs is a list within that workflow, and then steps is a list within that specific job. In this case, we have a single workflow containing one job and one step. And then there on line 8, the runs on key specifies what type of execution environment you want to have. Ubuntu 24.04 is a runner type hosted by GitHub itself. If you wanted to run on macOS or Windows, you would specify that here. Or if you wanted to run on a third-party service like Namespace, you would specify one of their runner types in this field. We'll go more into that later in the advanced section, but it's necessary to understand specifying Ubuntu 24.04 there means that we're going to get a runner hosted by GitHub running Ubuntu on that version. Let's jump over to GitHub in the browser and see this workflow in action. So if you go to the repo under the Actions tab, you'll see all the different workflows that you have within your repo here. If I go to the Hello World workflow, I can then click Run Workflow, and this button is only available because I have that workflow dispatch trigger in my workflow. I can run it from a particular branch. In this case, I'll run it from main. I'll click Run Workflow. Now if I refresh the page, we can see a run of that workflow has shown up. It's in a queued state, so it's waiting for a GitHub Action runner. If I click into it, we can see it has now executed, and it has run the command that I had in my step, hello, from an inline bash script in a GitHub Action workflow. So that's the most simple workflow you can have. Now, what are the different types of steps you can specify in a different workflow? Let's expand our Hello World workflow to have 3 jobs, each containing one step, and this will highlight the different types of steps that you can have. And so what have we actually changed here in this update? You can see in the first step, it's almost identical to before. We're executing an inline bash script. That's the default shell on the runner. In the second job, we've actually modified that to use the Python shell. So now instead of writing bash, we can write Python. And then in the third one, we're using a third-party open source action. This is the Hello World JavaScript action. And I've shown a screenshot here of that repo. And so we're able to leverage this external action to execute as a step within our job. And now let's jump over to our code editor and look at this workflow there. So as you can see, I made a few tweaks. I made this a little bit more verbose, so we know this is running from the bash script, this is running from the inline Python script, and here we're specifying that third-party action still, but rather than specify a version, we're actually going to tag the specific commit hash of the version we want to run. We're going to talk more about why that is from a security perspective and a stability perspective, but just know for now, you can specify either as a specific git tag or as a commit hash, but the commit hash is better practice. These longer strings didn't fit on the slide, that's why I didn't include them. Now we can jump into the GitHub user interface and run a copy of this. So I called this workflow step types, so we can navigate to it here, run it via the workflow dispatch, see that it's executing. Each of those 3 jobs is running in parallel. We can see they all succeeded and executed the commands that we expected. The Python executed accordingly. And that third-party action printed the output we would expect. Those are the 3 primary types of steps that you can run within your GitHub Action workflow, either bash, Python, or a GitHub Action as a step. However, there's one thing we haven't touched on here. You saw those 3 jobs ran in parallel. We can also tell GitHub Actions to structure these jobs in a specific order by adding dependencies in the form of needs within the job specification. So workflows form what's called a directed acyclic graph, or a DAG, and we can use that needs key to say which jobs depend on which other jobs. This will produce a structure like shown in that screenshot and allow us to take outputs from one job and pass them to another. So here I'm showing in the first job, we can run a sequence of steps. The second job, we can run an independent step, which is not connected to job 1 in any way. But then by using needs jobs 1 and 2 for job 3 and needs jobs 2 and 3 for job 4, we're going to ensure that jobs 1 and 2 execute first in parallel, then job 3, and then job 4. Let's jump over to the browser and run a copy of this. I called this workflow jobs and steps. We can run workflow, run. Clicking into it, we see that structure as specified within our YAML. Jobs 1 and 2 have completed, allowing job 3 to be picked up. And only after job 3 completes will we see job 4 execute. It is an acyclic graph, so you cannot have a loop. You need to have a flow in one direction. That's how you specify the structure of your jobs within a workflow. So far, we've been using the workflow dispatch as a manual trigger that we can utilize from within the GitHub interface. That one's actually less common, but it's useful for an educational setting like this. The types of events that I see used more frequently are highlighted here within this list of all the events. The first one we've been seeing that trigger manually with the workflow dispatch. The second one, push to a branch. So you can set it to trigger a workflow on a push to any branch, or you can filter to specific branches. For example, you might want to filter to your default or main branch. You can also, as I mentioned, trigger workflows based on a pull request event. So that could be the creation or update of a pull request. You could filter that so it only issues on pull request against a certain branch. There's lots of control here within how you structure these. And then the final one that I see most frequently is running on some timed cron schedules. Maybe you have something that runs nightly or weekly, and you're able to use this schedule type of a triggering event to specify that. Now I've written a simple workflow that leverages these different types of triggers. You could see, as I mentioned, the push workflow could be triggered only on a specific branch pattern. So we've got example branch and then a wildcard. So you can use glob patterns in those fields. Pull request, the default, if you don't specify a type of pull request event, it's going to be whenever one is opened, synchronized, or reopened. And then you can also specify within a pull request event which paths you want to trigger on. And so this enables you to, as you'll see later on, filter down so you're only executing workflows relevant to a specific subpath within your repo. This is critical if you're using a mono repo that's going to have multiple services defined within it to not have wasteful execution of your workflows. You can see how the cron schedules are defined here with a cron string. So by specifying the string 00 star star star, that's going to run at midnight UTC, so the 0th minute of the 0th hour every single day. That's what that means. And then we've seen the workflow dispatch already. That's just a manual trigger that you can execute either via the GitHub CLI or the web interface. In this example workflow, all I'm doing is taking the event that triggered the workflow and dumping that out to the terminal so that we can see all the different metadata that is associated with it that you can leverage from within the workflow as you perform your work. Now specifically, let's take a look at the pull request and the paths filtering to see how that would work. So within my repo, under the module 3 subdirectory, I have this filters directory, and within there we have an excluded file and an included file. My paths filters should include markdown files, but exclude text file. If I create a pull request that modifies the markdown file, it will execute this workflow. If I create a pull request that modifies only the text file, it will not execute it. So I've actually done that ahead of time. I've got these 2 pull requests here. This one, we've modified the markdown file to include the paths filter. So I'm going to copy this branch. I'm going to push to get an update to that PR. And then if we go back here, this workflow was triggered just a few seconds ago. We can go in and look at the event that triggered it. It's a big old JSON structure containing lots of information about the event that triggered it. So this is going to be things like the pull request number, the files that were modified, et cetera, et cetera. And so this is super useful as we go down the path of using these data to decide how our action is going to behave. Let's do the opposite and modify the file in that excluded filter. So if I go here and check out this one, Let's just make an empty commit and push. Looking at the files changed, we've modified this text file on our branch. We've pushed that empty commit. However, no additional actions were triggered. If we go back here to the Actions tab, no action was triggered. Now, why did this happen? We have prefixed that exclamation point on line 15. When we modify a file that matches that pattern, we don't need to trigger this workflow. So that's how you can start to use these paths to understand how you can trigger and control when workflows are triggered for specific updates. As I showed, each of these events contains tons of metadata associated with it, and you can tap into those data within your workflow itself. Just like with the pull request filter, path filters, I can go ahead and make a branch that matches my example branch and say git checkout -b. This will run workflow, git push. We see that it triggered a run of my workflow based on that branch name. However, if I make a different branch name, and I push that, we will not see an additional run because it didn't match any of the branch patterns specified in that list. When we get to the Capstone module of the course, you'll see how these are leveraged in practice across a variety of different use cases. The next core feature I want to touch on here are environment variables. These are variables within the execution environment, and these can be scoped to a variety of different levels. Each of those different concepts that we talked about, we can have an environment variable that is shared across the entire workflow. We can have one that is shared only within a job or only within a step. And so you can see here, I've specified one of each of those such that we can look at which are defined in which context. When we execute this, that workflow var will be available in any of our different steps. The job var will be available only in job number 1, and the step var will be only available in job 1, step 1. So let's go ahead and run this. That workflow is named environment variables, run workflow. We'll click in here. We see jobs 1 and 2. Because I didn't specify a needs key, these can run in parallel. Within job 1, we can see all 3 of these are visible and print appropriately. If we look at job 1, step 2, we would expect the workflow and the job var to be defined. However, the step var is unset here. And then if we look into job 2, now only the workflow scoped environment variable is going to be set, and the job and step variables, which were scoped to job 1, are not set. This is how you can control environment variables set within your workflow itself. We'll look at in a little bit how to store environment variables from one step and persist those throughout the life of a job. This is within your job configuration itself. Now, those environment variables were defined within our YAML file. We also can define things at runtime and pass data between steps and between jobs. And so we can do this via outputs and inputs. We also can do this via environment variables within a job itself. And so there's 3 kind of main things to showcase here. The first one is how to take some string and store it to an output, and then how to consume that from within another step. And the way that we do that is we write to this file at the path specified by GitHub output. GitHub's going to populate that environment variable for us. We're going to echo foo equals bar in this case. That double greater than sign is going to append to the end of that file. And now we can reference that in other steps. And so on line 26, we can say from the step with the ID generate foo, look at the outputs and use the foo output. So line 26 is going to output foo bar. For environment variables, it's very similar, but instead of writing to the GitHub output file, we write to the GitHub end file. Within a job, we can then reference that as a normal shell variable. So like on line 25, we've got $foo. And then to pass things across jobs, so interjob, we first need to put it as an output of the step, like before. We then need to reference the job as an output of the job, so line 10 does that. And then in the consuming job, we need to specify the needs key with the upstream job in it. And then finally, we can reference it from that list of upstream jobs based on the name, the outputs, and the key with which it's referenced. So if we go and run this, we'll see on lines 25 and 26, those 2 will both be set. But then on lines 34 and 35, only line 34 will be set, whereas line 35 with the environment variable, that does not persist across jobs. This workflow is named passing variables between jobs. We'll run it. As we expect, our producer is upstream of the consumer because we specified that needs key. Here we're generating those data. We're setting foo equal to bar and setting both our output and our environment variable. Now, when we inspect the values, we can see they're both properly set to bar. In our consumer job, if we look at it, only the value which was passed from output to input persisted. That's because environment variables do not persist across jobs because they're run in different compute environments. So you need to be explicit about which data you're passing from one job to another. Now, the last feature that I want to touch on in this core features module are secrets and variables. So these are very similar to the environment variables that we saw before. However, these can be stored and managed at a few different levels. So you can store them either at the GitHub organization level, a repository within that organization, or even a specific environment within a repository. So think about staging versus production might have different credentials for the deployment environment that you're going to deploy your application to. This allows you to do that. For sensitive values, like a database password or a credential, those would go as secrets. And those you can only set within the UI. You can't actually read them back except within the context of a GitHub action. For non-sensitive values that you want to be able to view and edit, those can be set as variables from within the UI. You can see those, update them, and consume them from within your actions. To set these, you go under the Settings tab, and then under Actions and Secrets and Variables. You can then populate them either for an environment or for the repository. You could do the same at the organization level to share secrets across different repos. And then for the non-sensitive variables input, you click onto that Variables tab, and then you're able to specify them there. Within a workflow, you use that $ double curly braces syntax. For secrets, it's going to be secrets dot and then the name of the secret. For variables, it's going to be vars dot and then the name of the variable. So within my repo, under secrets and variables, actions, you can see I've specified a staging and production secret. So these are two different values stored at the same key for different environments. I then also have a repository secret, as well as some AWS secrets that we'll use later on. Finally, in the variable side, we have a staging and production environment variable, non-sensitive, and you can see the value specified here. And then we also have one at the repository level that will be shared across any environment. So if we go to our actions, scroll down to secrets and environments, click run, you can see I have two different jobs here. If we jump back to the definition, on lines 8 and lines 26, I'm specifying the environment in which this is running. So the top job is going to use that staging environment secret and variable, and the bottom job is going to use the production environment secret and variable. Let's click into the staging one and inspect the values of the job. Now you'll notice when we try to print out a secret value, GitHub automatically masks it using these asterisks. That's to prevent us from accidentally leaking our credentials or sensitive values into the logs of our jobs. We also see that it output the repository variable and the staging variable. So if we go to the production job, we'll see, hopefully, this repo variable will be identical, but this should say this is the production environment variable value. And that's exactly what we see. The repo variable was the same across these two different environment runs. However, within the job that specified the environment as production, we got the production specific value of that environment variable and that secret. Before we wrap up this module, I do want to call out a feature that we've already used a couple times, but I wanted to address it a little bit more explicitly, and that is contexts. So within GitHub Actions, there's all these different contexts that you have access to at runtime, and you access them using that $ double curly braces syntax. So far, we've seen the needs and the steps contexts. We use those when passing data from one step to another or from one job to another. And then we just saw how to use the secrets and vars context to load those data into our runner. I've listed here at the bottom a number of additional contexts, including the GitHub context. That'll have things about the run and the repo state. The environment context will have all the environment variables set within the workflow job or step level. The matrix context, which we'll use in the future to execute multiple copies of jobs. The job context, which will have our current job status, as well as some information about containers and services. The runner context, which has info about the runner itself. And finally, the inputs context, where you can provide inputs to your workflow and then use those at runtime. Now we can move from those sort of basic core features of GitHub Actions into some of what I would consider the more advanced features. Now, not all of these are going to be difficult to use, but these are things that extend your ability to utilize the platform versus needing to use them right from the start. Like in Module 3, these are still just a distilled version of each of these features, trying to capture their essence without getting bogged down too much in the weeds. We'll see how to use them for real-world examples as we move on later in the course and into the capstone. The first feature that I want to highlight here are the runner types. Now, when I was describing the most basic Hello World workflow, we still utilize the runs on field to specify what type of runner, but now we can look at the different types that are available. There's GitHub hosted runners. These are things like Ubuntu 24.04, Windows and Mac OS runners from GitHub. There's third-party hosted runners. Now, these are going to be companies like Namespace, where you can utilize their infrastructure to execute your builds. And why would you want to do something like this? Oftentimes, they're able to offer significantly faster compute and storage at a reduced price relative to the hosted runners. It also opens up the possibility to utilize their infrastructure for things like faster caching, better observability, and improved multi-architecture container build experiences. The third category is self-hosted. So the actual runner agent is an open source project, which you can install into a server yourself or run in something like Kubernetes with the Actions runner controller or Arc project. There's also a really cool project called RunsOn, which deploys a set of infrastructure into your own AWS account, which can spin up on-demand EC2 instances for each runner job, which can reduce the costs of execution even further, while also keeping the data within your own VPC. By specifying a runner type, you're controlling which virtual machine image, the operating system plus the dependencies, which are going to be included in that environment, as well as the CPU and memory that are going to be available. You can see a number of examples here on the right, including the Ubuntu, Windows, and Mac OS runners from GitHub itself. There's also an option to execute your jobs within a container image. So by specifying both a runs-on and a container.image, you're able to provide a container image with additional dependencies, which might not be available in that base image. And then you can also specify a group or labels, which you can apply to different runner types, which allow you to control things like how many CPU cores or how much memory a particular runner might have. In the third-party hosted runner section, you can see a few examples from Namespace. When you first create a Namespace account, you'll have something like Namespace profile default available. You can also append the ARM64 string to the end to get an ARM instance. Or you can provide your own custom image where you can install dependencies ahead of time to provide exactly the set of dependencies your build needs without the need to install or modify them with each run. Now finally, for a self-hosted runner, you can name those runners anything you want. And so here, as an example, I've just named it my self-hosted runner name. I'm not going to do a deep dive on self-hosted runners. That could be a video in and of itself, and perhaps I'll do that. But within this course, you see me use a lot of GitHub hosted runners, and moving forward, you'll see me use those namespace runners quite a bit. Let's go ahead and jump over to GitHub and execute this workflow. I name this workflow runner types. We can click run. I have these three jobs at the top, which are executing on GitHub infrastructure. I've got this one, which is running on a GitHub virtual machine, but inside of an Alpine container. And then finally, I've got this namespace VM. I'll show you if I go into my namespace account by logging in and go to profiles, this default one is provided out of the box, as well as this ARM64 image. Now these were two that I created custom with various dependencies pre-installed or with particular cache configurations enabled. To use this default runner, I just specify namespace profile default as my runs on field. If we click into one of these, we can validate that it is running what we expect. You can see hello from Linux x64, hello from macOS ARM64, and this one, since it's running inside that container, is hello from Linux x64, but it shows us the container name of Alpine Linux. And finally, clicking into our namespace job, we can see it's also an x64 Linux runner. However, it's specifying the runner type as NSC for namespace cloud, runner, and then that identifier string. Now, if we look at the different runner types available, I mentioned that one of the reasons you might choose a third-party option is because they provide less expensive, more capable runners. As we can see here, this is a benchmark performed by RunsOn across many of the different providers, including GitHub, third-party, or self-hosted via RunsOn. As you can see, for these x64 runners, the namespace runners are at the very top in terms of performance and are also only half the cost of the hosted GitHub ones. I also added a circle for good developer experience because Namespace provides some really nice features around developer experience just for using their runners. If we click into my Namespace profile and I go to jobs, I can see all the jobs that have run, but if I go to insights, now I can start to see the execution timing for my job over time. I can filter down to a particular job and start to see how that performance is trending. If I click into a specific job, I can see CPU, memory, network, and storage performance within that execution, as well as logs from that runner as it executed. And so I encourage you to check them out. There's a link in the description that will take you there. Definitely let them know that you found them through this video and say thank you for enabling me to create and distribute this content for free. Another feature that we haven't touched on yet is persisting data outside the context of their ephemeral runner. So by default, jobs are run in these ephemeral environments that are created and destroyed with the lifecycle of the job itself. Artifacts give us a mechanism to persist data beyond that lifecycle. There are 2 official actions provided by GitHub that we can use to both store and then consume artifacts. To upload artifacts, we use action/upload artifact, and to consume an artifact, we use the download artifact action. As you can see in my workflow here on the right, I'm going to create a text file. I then upload it as an artifact, and then in a downstream job, I'm able to download that text file and cat it out to the terminal. Artifacts also show up in the GitHub UI, so they can be useful for storing things like test results or other files that you might want to keep a record of across runs. We can jump over to GitHub and execute this. The workflow name is artifact. We've got our producing job and then our consuming job. So we took this string, stored it in an artifact.txt file, specified that is the file we wanted to upload. Then in our consumer, we specified which artifact we wanted to pull, and then we catted that file to the terminal. If we go back to this workflow run, we can see in the UI, this is an artifact that was produced at runtime. We could download it. It's a zip file. If I open it up, here are the contents that we stored in that artifact. And this will persist such that if we needed to refer back to it for some reason, we could find the specific artifact associated with this workflow run in the future. Now, a similar but slightly different need to persist data across jobs is for caching. And so again, jobs are ephemeral environments. So if we need to install or modify something within that job, we either need to do it every single time the job runs, or we can use a cache to persist those data elsewhere and then restore them to avoid doing that repetitive work over and over. GitHub provides an official caching action/cache. When you use that, data that you specify will be uploaded into a remote object storage that's going to be in Azure by default. And within GitHub, their cache is going to be capped at 10 gigabytes. If you go over that 10 gigabytes, it will evict stale data such that you will sort of have this rolling 10 gigabyte window of your cache usage. As you can see from the workflow definition, we're going to start by attempting to restore the cache. If you've never run your workflow before, that would be a cache miss to start. Then on line 20, we can check if it was a hit or a miss. If it was a hit, then we can skip this step. If it was a miss, we will generate a file to then cache for future runs. We then have a step that says if it was a miss, we do want to populate that cache. And then finally, we're just outputting whether or not it was a hit and catting that file to the... Now, the types of things that you probably want to cache here, either things like your language runtime or toolchain that you'll need to build and execute your application, or things like dependencies that you're downloading and including in your application builds. Let's go ahead and jump over to GitHub and see this workflow run. The workflow is named caching. We'll run it. Now, as you can see, this is the first time I've executed this workflow in a long time. So any results that had been cached have been since evicted. It says cache not found. So we then created the file and stored it. Now, if we go back and run it again, we should see a hit for that same key. Under the restore cache step, we see that it found our cache successfully. And then it was able to skip these 2 steps, which were conditional to only run if it was a cache miss. This showed how to cache specific paths or files within your runner. However, for many common languages and language toolchains, your cache configuration will depend on how those languages store dependencies. For example, when you run the official setup node action, you can configure it to cache your NPM dependencies as follows. For this example, I have just a super minimal Node.js project, which I can show in a second. We're running setup node with a specific version, and then we're configuring the cache of type NPM, and specifically telling it where within our repository the package.lock.json file lives. This configures things so that when we later run our npm install, we will automatically cache those node modules that get installed, such that across runs, as long as those dependencies don't change, we should see a significant speed up and avoid needing to re-download those with every execution. So here is the minimal node project. Within my package.json, I just have a single dependency of leftpad, and then my lock file similarly has that single dependency included. As you saw in the workflow from the slide, we're checking out the code. We're running setup node with our specific caching configuration. We're telling it where the lock file lives. That's how it generates an appropriate cache key before installing our dependencies and listing out the modules that have been installed. If we go back and look at those runs that we executed before, in the first run, there was no npm cache. But in the second run, we had a cache hit, and we were able to download that dependency from our cache rather than needing to pull it from npm directly. So that's a node example. On the left, you can see the documentation for how this would look with Go. And each language is going to be slightly different in terms of where it stores its dependencies and how you should configure an appropriate cache key. Now, caching is another thing that Namespace does a bit differently. So far, we've been using those object stored based caches where you're telling it a specific set of files and a specific cache key. And it's a deterministic thing where you're going to upload those files. And if you have a cache key hit, you will pull them down at runtime. However, Namespace takes a little bit different of an approach. You can configure what's called a cache volume, and rather than upload and download explicitly from a object store, it's going to snapshot your volume after you've completed, and then you can mount in a copy of that volume to each of your jobs to avoid that extra time of uploading and downloading these cached artifacts. It's going to be a bit less deterministic. However, because of the types of things that you're caching, where you're often installing a set of dependencies over and over, usually that turns out fine. I created a simple example to sort of benchmark this, where I have one job which creates a single very large file and uploads that to the GitHub Actions cache, as well as uses a namespace cache volume. And then I have another job which generates thousands and thousands of very small files and does the same thing. As you can see, when you get a cache hit across them, the namespace cloud cache performs significantly better than the GitHub Actions cache because you don't have to spend that time uploading and downloading those data. Because you're not specifying an explicit cache key, you could have a cache miss occasionally, but the penalty there is just a little bit of extra runtime, whereas the benefit would be a significant speed up on nearly every single run. Let's take a look at how this workflow is defined. Here I'm using a set of tags that will allow me to get a namespace runner with the appropriate image type using 4 CPU and 16 gigabytes of memory. And then I'm specifying the cache volume characteristics that I want. Here it's 20 gigabytes, and I'm using this as sort of a unique volume type to separate my large test from my many test. I run the provided cache action step from namespace to set up my cache volume. I then check if the file exists that I'm looking for. If it doesn't exist, I generate a single large file, and then I validate that the file exists afterwards. So if it was a cache hit, this should return true. If it was not a cache hit, it will get generated above. Now for the many test, it's similar. The only difference is that I use this small count environment variable specified above. So here I'm generating 100,000 files, each of size 4,096 bytes, and then validating that those exist. The GitHub Actions versions are pretty much identical, with the only difference being that rather than using the namespace caching, I'm using the official GitHub Actions caching. We can look at my first run of this workflow here, where all of these caches miss, and you can see the single large file takes about 10 and 20 seconds respectively on namespace and GitHub Actions, and then the version where we generated 100,000 files takes 1:43 and 2 minutes and 11. A lot of that time is spent generating those files and then uploading them to that object store cache in this case. When we look at the next execution of this workflow, in this case, we had a cache hit for all of them, which is great, but we see the namespace instances took 3 and 4 seconds respectively, whereas the GitHub Actions cache took 28 and 12 seconds respectively. And so as you think about caching, this is a really unique approach that Namespace has taken here. It does require adding a step to your workflow to set up that cache. However, it can pay huge dividends in terms of not performing repeated work and avoiding that upload download time that you need to use an object store-based cache. Moving on from caching, another critical feature that GitHub provides is the ability to scope what permissions your workflow has to the GitHub API. And so by default, you're going to have contents and packages read-only permissions. The contents permissions will allow you to pull the code itself, which is going to be key for doing anything with your application. And then the packages is for the GitHub package registry. You'll be able to read from there. There are additional permissions associated with all the different types of entities shown here on the left. And you can have either read, write, or none. And the default is to have none for all of these except for contents and packages. I've written a workflow on the right-hand side to just showcase how this works. In our first job, we have specified that we only have read permissions for pull requests and nothing else. I then designed my job to both list the PRs in the repo, as well as attempt to make an edit to one of those PRs by adding a label. That first run on line 16 will succeed. The second command on line 23 will fail because we don't have that write access. Now in the second job, I'm specifying that we do have write access for the pull requests. Running that same command, we're able to successfully run the add label command, which will apply a documentation label to that specific PR. And just as a detail, the GitHub CLI uses the environment variable gh_token for its authentication. That's why I'm taking that github.token provided by our runner and storing it in that environment variable for those different steps. Let's go ahead and see this run. Now I'll start by removing this label. Now we can go under Actions and Permissions, run the workflow. We can see the read-only PR job failed as expected. We were able to successfully list the PRs, but when we attempted to add that label, we got an error that the resource was not accessible via the integration. If we go to the read-write PR that had the appropriate permissions, now when we add that label, this command succeeded. If we go to our pull request, that documentation label has been added back. So this gives us fine-grained control over what within GitHub our workflows will be able to execute. In general, you should always scope the permissions to the minimum set that are required. Most workflows are going to need contents read access. Some are going to need packages read access. And only if you're taking these other actions against these other entities would you want to specify additional permissions. So if that feature allows us to control access to GitHub systems, how do we control access to third-party systems? There's two primary mechanisms where we can authenticate to a third-party system. The first of which is a static credential. Think of this as like an API key. This would be a long-lived credential that you would store in one of those GitHub Action secrets we talked about in the previous module. It is less secure because it's a long-lived credential. And so if that were to leak, someone might be able to use it. However, it is compatible with pretty much every platform. Any software platform you're accessing over the web is likely going to have a way to provide an API key or a static credential. Now, a better, more secure approach is what's known as an OIDC token. OIDC stands for OpenID Connect, and it is a short-lived credential which you will retrieve at runtime. Because of the fact that it's short-lived, it's more secure. If it were to leak after the fact, it would no longer be active and wouldn't matter. However, it does require that third-party service to support OIDC in the first place. I'm going to use AWS as an example of how we can use both of these mechanisms to authenticate. The first one is going to use a static credential. While this course isn't about AWS, I can show you how I can generate a static key for AWS quickly within the console. And then the second approach, we'll use that OIDC approach, which is a little bit more complex to set up, but not too bad. And it's really the way you should be doing this in production systems. So here I'm logged into an AWS account, and I have a user called the GitHub Actions user. This user doesn't have any permissions really, so I just want to be able to authenticate as them and verify that I am authenticated in that way. However, under security credentials, you can go here to access keys. You can do create access key. You can specify what type it is, etc. And say GitHub Actions static key, create access key. You could then copy these and paste them into the secrets interface. So if we go here under settings, secrets and variables, actions, and then we have AWS access key and AWS secret key. So you would take those values from here and here and paste them in. Then within our workflow, we can use the official AWS Actions configure AWS credentials action and pass it the access key and secret access key as well as the region we want to authenticate to. And this will authenticate against that user using that static key. I show you this for completeness, but as I mentioned, really, if it is available, you should be using the OIDC approach. Here are the documentations on setting up that OpenID Connect with AWS. So specifically, you have to add the OIDC provider within the AWS IAM configuration. We can click into these docs and follow these steps. The way that you do that is under IAM, Identity Providers, click Add Provider, OpenID Connect. It then gives you the provider URL and audience. This is the provider URL. This is the audience. We then need to specify an IAM role that our GitHub action will be able to assume. So I can go back over here. I've already done this, which is why I didn't create that, but you can see my provider here with my audience. Now under roles, I have this GitHub Actions role that I've created. And in order to assume this role, we need to add a trust relationship, which says we are federating access to this role based on the OIDC provider. This is pointing to that provider that we just specified. I'm going to give it the ability to assume my role with the audience that I specified for that provider. And then finally, this is how I can lock down access to a specific repo or user. So in this case, only repos that I own will be able to access this role. And so with those things set up, the OIDC identity provider, as well as this role with the appropriate trust policy, I can now run the same configure AWS credentials action, but instead of needing to pass it that secret access key, I can just specify the role that I want to assume. There is one important note here, and that is this 21. The ID token permission must be set to write in order for us to successfully request a JWT and use it for that OIDC authentication. And so it's not that much more complex, but it's much more secure. So if you're going to authenticate to a system which does have this support, you should use the OIDC approach. If not, you can always fall back to a static credential as shown above. Let's go ahead and run this workflow just to showcase that it works. It's called third-party auth, run workflow, run. We successfully authenticated here, and we successfully authenticated against our role here. Now, the final feature set that I want to highlight in this section is matrix and conditionals. So matrix provides us the ability to run multiple copies of a job with different input configurations. And then conditionals allow us to specify an if statement that allows steps to either run or not run, or jobs to run or not run based on the value of variables within our workflow. Now, finally, concurrency controls how multiple runs of the same workflow should be handled. So if we're triggering the same workflow, let's say based on multiple commits to our repo, allows us to specify which of those runs should be grouped together. And then within a group, should you cancel those runs or allow them to continue executing? This can avoid wasted compute for runs which are meaningless if they've been superseded with more recent code. To highlight these, I created a simple workflow that has two jobs. The first of which is a matrix job. And so under that strategy matrix key, we can provide a set of inputs. Here we have number 1 and 2, as well as letter A, B, C. And then GitHub Actions will take all of those combinations. So we'll have 1A, 1B, 1C, 2A, 2B, 2C. And then finally, we have this exclude key, which says run all 6 of those combinations, except don't run 1C. So we should see 5 different jobs running in parallel, executing those different combinations. To highlight the conditional aspect, also within step 2, I've added this if statement saying if matrix number equals 2 and matrix letter equals C, skip that job. So we'll see 5 jobs running in parallel, and within one of those jobs, we'll see this step specifically skipped. To highlight our concurrency setting, I've grouped by GitHub workflow, so that's the workflow name, as well as the GitHub ref, so that's going to be like my branch or my tag, such that if we push to the same branch multiple times while the old job is running, it will cancel that older job. This is why I've included that sleep job at the bottom, so the execution takes long enough to give us time to come back, issue a new commit, and force this to cancel the old run. So let's go ahead and see this in action. We'll go to matrix and conditionals. We'll start by triggering one. Here, that first one is. We see those 5 jobs executed, 1A, 1B. We skipped 1C, remember. Now we have 2A, 2B, and 2C. But if we click into 2C, based on that conditional I had specified there, we're going to skip that specific step. Now let's take a look at how the concurrency works. So this one is still running because that sleep job is specified to sleep for 100 seconds. We'll trigger another run of this workflow. And because that concurrency group is going to match, because it's the same workflow and it's off of the main branch, it's waiting for GitHub to then cancel this older run. We see status canceled. And now the newer run will take over and execute. I kind of sped through these features, but these are really powerful features that allow us to control the execution of the workflow at runtime. And we're going to leverage these heavily as we move into the Capstone project and start to do things within our mono repo to fan out jobs across the different services and only execute the jobs and steps which need to be run for each of them. Now, so far, we've mostly focused on our workflows and all the features that GitHub Actions has for authoring those. Now we're going to spend the next few modules looking at individual actions. So if you think back to module 3, where I showcased the different types of steps you can write, a step can either be an inline bash script, an inline Python script, or it can be an action. And so an action is going to be a separate application which runs as a step within one of your workflows. One of the key features that differentiates GitHub Actions from some of the other competitors is the huge public marketplace. And so in this module, we'll take a look at that public marketplace and how to utilize actions that exist there. If you go to github.com/marketplace and then search for type actions, you'll see a listing of all the public actions that are available there. You can then sort them by various features and search for the type of action that you want. We'll go to my browser and navigate there now. So here I am on the GitHub Actions marketplace. As you can see, there's lots of different actions available. If I scroll to the bottom, there's over 500 pages of them. We've already used some of these. For example, the checkout action is the official action from GitHub to check out your code from your repository. To use any action, within your step definition, you'll have the uses key and then a path to the repo where it lives. In this case, this is the actions organization and the checkout repo. So while we can see it on the marketplace, we can also see the Git repo associated with this if we go down here and click View Source Code. You'll notice that because that was an official action from GitHub, it has this blue verified check mark. Let's imagine our project was using Cypress for end-to-end tests. Let's search for Cypress. There's this action from the Cypress organization itself, as well as a number of other actions for doing various things with Cypress. Let's click in here, and we can see they're going to set up things like installing our dependencies, handling caching. So rather than need to author all this ourselves, we could likely tap into this action, add it to our workflow with just a couple of lines, and get our Cypress test running within GitHub just that easy. Now, as I look at these third-party actions, there's a number of signals I'm using to decide if I want to use it or not. In general, I'm going to assess it like any open source dependency that I might pull into my application. The number one criteria is, does this action do what I want it to do? Is it providing value to me? And is that value worthwhile enough for me to want to use it instead of authoring that capability myself. In terms of the quality and trustworthiness, there's a number of things you can look for. There's that blue check mark, which means that GitHub has verified the identity of the organization or user who has authored that action. That can be one signal of a more trustworthy action. Now, not every action that you want to use is going to be verified in this way, but that's just one signal you can use. The number of stars, just like an open source project, shows how popular a project is. The higher the number of stars, the more likely it is that lots of people are using and verifying the capabilities of that action as described. And then finally, is this an active project? If you look into the repo, as I showed you, as you click into that repo and look at the commit history, are there commits in the last week or few weeks, or has it been stagnant for many years? I'm much more likely to use an action which has an active history, and it seems that the authors are continuing to update and address potential issues as they may arise. Early in the course, when I used third-party actions, you saw that I tagged it with the specific commit hash rather than a version. Now, any of these four syntax will work. On line 2, it would just use the latest version available. On line 3, it would use the latest major version 4. Line 4 is going to use that specific git tag of 4.2.2, but then line 5, I get a specific commit within that repo. This is important because these are third-party dependencies. The only way within GitHub Actions to ensure that you're running the exact same version is to pin to the commit hash. It may seem like pinning to a specific git tag is sufficient. However, there have been incidents where a malicious actor took over a repo where a GitHub action lived, wiped all of those git tags and pushed a malicious commit, and then re-tagged every single historical tag to that malicious commit to exfiltrate secrets. That's why I always recommend that you should pin to the specific commit hash, because that can't be modified after the fact. And so it guarantees you will keep that same version and you wouldn't be impacted by something like that. I also add a comment with the tag that that commit points to, just to make it clear to future readers which version or release of that action is running. Now I'll quickly highlight a handful of popular actions that I have seen used broadly across the projects that I've worked on. As I mentioned, GitHub itself provides a number of official actions. These are things that most every repo is going to leverage, things like checking out your code, caching, as we saw in the previous module, using that artifact upload and download to store artifacts from within a workflow run. And then this last one, GitHub script, provides an interface to very easily make calls to the GitHub API via action that takes as an input an asynchronous JavaScript function. So if you need to do something to interact with some GitHub entity, like maybe add a comment to a PR based on the results of your workflow, the GitHub script action is one easy way to do that. Another category of actions that are very popular and are used in almost every project that I've worked on are actions to install the runtimes and dependencies that you may need for your continuous integration workflows. These are 3 examples, which all come from the official GitHub organization. The first one is to set up Node.js, the second one to set up Go, and the third one to set up the Java development kit. These are going to contain utilities for things like configuring caching appropriately, making sure that you have the right version of your language, and including the common software that you would need in that language toolchain. Another popular project is the superlinter. This is an application that has linting capabilities across a huge variety of different languages. So you can use this single action to lint across any of the languages that you're using within your project, which can be quite convenient. And then just a few more here that I see used all the time are building and pushing your container images. There's an official action as well as one from Docker. This will include things like authenticating to your registry, passing it the appropriate tags, and telling it where your build configurations live to then go off and build and push your container images. These also oftentimes contain utilities for handling multi-architecture builds. And then finally, for authenticating to third-party systems, many organizations will provide an action that makes that much easier. I showcased this with AWS in the previous module, but Azure and GCP also provide their own authentication actions. And so rather than needing to download the appropriate CLI and manually pass in the credentials, these are configured to make that much easier to streamline your usage of those platforms from within a GitHub Actions workflow. Throughout the rest of the course, you'll see me actually use a number of these actions as we build out the various workflows for our Capstone project. In the previous module, we saw how to consume these marketplace actions. Now let's take a look at how to author our own first-party actions. There's a handful of mechanisms within GitHub Actions that we can use to write and reuse our logic across workflows. The 4 that I'm going to be covering here are composite actions, reusable workflows, JavaScript and TypeScript actions, and then container actions, which actually allow you to write your actions in any language that you'd like. A composite action is the easiest way to bundle up logic that you want to reuse across multiple workflows or across different jobs within the same workflow. All you need to do to create a composite action is create an action.yaml file. This file is going to look very similar to the workflow files that you're used to, except it's going to optionally include a set of inputs, a set of outputs, and then a list of all the steps that you want to execute within it. Once you have that composite action defined, to consume it, you use the uses syntax and pass a relative path to that composite action within the repo. In this example, I have a very simple hello world composite action. It's going to do two things. It's going to take an input string of who to greet and print that out to the console. It's then also going to generate a random number and provide that as an output to the action. To showcase utilizing this, I've written a simple workflow on the right-hand side, which takes this composite action and consumes it in two separate jobs with slightly different input strings. And then we also echo out that random number just to showcase that they're going to be different. It's important to note that we do have the actions checkout step there on lines 10 and lines 23. This is what's going to pull down the source code where that action.yaml lives and allows us to use it within our workflow. Let's go to GitHub and run this workflow to see it in action. I called my workflow composite action demo, run workflow. We've got our two jobs. In our first job, we can see that we input who to greet as from composite action in hello world 1. And we got that echoed out to our terminal. And then we can see that the random number passed as an output from our composite action was 13829. If we go to the second job, we ran our composite action, but we passed a different input string with this hello world 2. That was echoed out to the terminal. And our random number is different with 10,129. Now in the repo for the course, I stored the action in the directory associated with this module. Normally though, I would store actions like this under the .github/actions directory, which is a nice convention so that you can go there and find all the actions associated with a particular repo. Now the next mechanism for reusing logic across workflows is what's known as a reusable workflow. Now technically this isn't a GitHub action, it is a workflow, and it runs as a job within another workflow rather than as a step. However, the reason you use a reusable workflow to take logic that you want to share across different executions of a workflow is quite similar in nature to these others, and which is why I included it in this section. On the right-hand side, you can see I've defined the source for this reusable workflow. This is going to use the same approach as all the other workflows we've seen thus far. However, the key distinction here is on line 4, and it uses that workflow call trigger, which is what indicates that it is a reusable workflow. Is going to be called from another workflow. Like our composite action, we're going to optionally have a set of inputs, and then there on line 13, we can define which secrets need to be passed into our workflow. It is important to note you can only pass repository or org level secrets in this fashion. If you want to access an environment secret, on the consumer side, you need to specify that environment, and then also indicate that you want to inherit those secrets. An example of this is in our caller workflow there on the left. So this caller workflow is going to execute two copies of this source workflow. The first one, we're running with that staging environment and we're telling it that we want to inherit the secrets from our environment. And in the second one, because we haven't specified that we'd like to inherit, we will not pick up any secrets from the production environment and will only have access to that explicit example repository secret that we're passing directly. There's also two ways to reference these. On line 9, this is similar to with the composite action where we have a relative path to the workflow in our repo. This will follow along. We use the current commit within a repository as the source definition. Whereas on line 17, we're passing an explicit git reference to the repo and the commit hash, which allows us to pin it to its particular version and have more control over when it upgrades. Let's go to GitHub and run a copy of this caller workflow. Even though both of these are workflows, we wouldn't call that source workflow directly. Instead, we want to run the caller workflow, which will run our source workflow as jobs within it. So I'll navigate to reusable workflow caller, run workflow. We get the two copies of our job. I'll click into the staging one. And remember, in this case, I told it to inherit the secrets that are available. And so this example environment secret is defined, although it's masked. If we click into our production environment job, in that one, I did not tell it to inherit the secrets. And so by default, it will not inherit my environment secrets. The repository secret is available there because I passed it explicitly. So when would I want to use just a normal standard workflow versus a composite action versus a reusable workflow? I made this little flowchart to showcase how I think about these things. The first question I would ask is, do you need to reuse this logic across multiple repos and or workflows? If the answer is no, you can just use a standard workflow. There's no benefit to moving this logic into one of these other approaches. If the answer is yes, then you need to further ask yourself, do you need to enforce standardization across the entire workflow itself? If the answer is yes, you want to go with a reusable workflow where you define that entire workflow and the only modifications are going to be the input values. If you don't need to enforce that level of standardization, a composite action is a slightly lighter weight and more flexible approach where you can bundle up just a subset of the logic while still avoiding copy pasting across a bunch of different places. As you think about your organization's needs and specific continuous integration workflows, Hopefully this helps you decide what logic should live where. Moving on to the third type of action, we have JavaScript and TypeScript actions. Now this is the type that GitHub Actions supports most natively, and many of the actions that you encounter on the marketplace or otherwise will be of this type. GitHub provides an NPM package called Actions Core that you will install as a dependency into a JavaScript or TypeScript project. You can then import that, and that will contain many different utilities for interacting with GitHub and GitHub Actions. Just like with the composite action, you'll include an action.yaml file that defines the metadata for your action, including optional inputs and outputs. And then you'll notice at the bottom there under the runs key, you'll specify which runtime to utilize. In this case, it will be a Node.js runtime, and then you need to specify where your main function lives. Now, regardless of whether you're authoring your action in JavaScript or TypeScript, you must package it as JavaScript. This means that if you're writing as TypeScript, you're going to have a build step where you turn that TypeScript and bundle it as JavaScript for consumption. GitHub provides a template repo for both the JavaScript action as well as a TypeScript action. I've taken both of these, added them as submodules to the course repo to showcase how they work. There's a third option of writing a JavaScript action with no build step. You check in all your dependencies as node modules, but I wouldn't suggest that. I would generally recommend going with a TypeScript action, which is going to have that build step, which is going to transpile your TypeScript into JavaScript and bundle all those dependencies alongside your action code. This will be more reliable and allows you to utilize types to make it easier to maintain and validate your action as you develop it. I'll jump to my code editor and show you what this looks like. Under Module 6, JavaScript Actions, TypeScript Action with Build, I've added a copy of that template repo that I was just showing as a submodule to the course repo. We can take a look at the action.yaml, which is just like I showed on the slide. Here we're running Node.js 20, and my main function lives in this dist/index.js. Now you'll notice I have my source files here written in TypeScript. The majority of my logic lives in this main.ts, which is exported and run from within my index.ts, and my build step is defined within my package.json. So under scripts, these are all scripts that were provided in that template repo. The build step is defined here in this package command, which is going to use a tool called rollup to take my TypeScript and all of the dependencies associated with my project and build them according to my configuration defined here. It's taking as my primary input that index.ts file, and then providing as my output in the dist directory an index.js file with a source map using ES modules. Let's take a look at this main function and maybe make a slight tweak to show you what the process was. As I noted, we're importing this actions core npm package from GitHub with methods like core.debug. So this is a debug log, and core.setOutput, where we can set the output of our action step. Let's add another log here. It says, hello, this is another info level log. I'll save it. However, this only exists in the TypeScript file currently. Let's go ahead and bundle our code so that will get propagated into the necessary JavaScript. For that, I can do npm run bundle. If I look at the git diff, here's the change I just made to the TypeScript file. But then because we bundled it, we now have a modification to our generated JavaScript file and to the source map. I can then commit these to the repo, then update the submodule reference to be for that latest commit. And now let's go ahead and run that. Now this JavaScript Actions workflow contains 3 jobs. One using a no-build JavaScript action, which exists in the repo, you can check it out. But as I mentioned, I wouldn't use that approach. Another one using a JavaScript action that does have a build step. And then thirdly, the TypeScript action, which is referencing the project, which I just modified. And so this is the one that we're going to want to look at. We'll go to Actions, JavaScript Actions, run workflow. That info level log line that we added now shows up here. Now the last type of action that I'll cover here is a container-based action. Because a container can leverage whatever runtime or language we'd like. So if our team is a bunch of engineers who are experts in Python, but don't really write TypeScript ever, we may want to author our actions accordingly. There also could be dependencies or packages that we want to pull in to perform some type of work that have a much stronger ecosystem within a particular language. Here within the action.yaml, you can see on line 12, rather than using the Node.js runtime, we're specifying that it's using Docker. And then for the image, you can either specify Docker file, which will build the Docker file each run, or you can specify container image at a particular tag. Option A is great for testing and validating because it will dynamically build the current state of the repo. However, needing to rebuild the action image with each build is a bunch of wasted effort and time. For production workflow that you care about speed and performance, you'll likely want to have a process by which you build that container image and push it to your registry and reference it directly. The process by which we extract things like inputs into a container image is a little bit clunky. As you see here, this action has the input who to greet, which is going to be a string. And within Python, I either need to load it from this magic environment variable that GitHub is populating, which would be input underscore and then the name of the input in all caps snake case, or I can pull it out of the args list using something like sys.argv. Also, there's no official GitHub package for languages other than JavaScript. So in order to interact with GitHub Actions, I end up having to print these magic strings to console using things like : notice there on line 18, rather than being able to use a specific method from that core package that we had in JavaScript. To write to an output is shown here on line 21, where I need to open the file that is at that GitHub output path and then append any information to it, similarly to how we did before when writing to it in Bash. Now finally, I need to bundle this up in a Docker file, which will vary based on the language that I'm writing my action in. In this case, because I don't have any dependencies, I'm simply starting from the Python base image, copying in my entry point Python script, and then setting the entry point that will run when the container is executed. If I did have additional dependencies, this Docker file would need to account for that by doing things like copying in a requirements file, running a pip install, or whatever other package manager I might be using like Poetry, etc. Now within the repo, under module 6, container actions, I have 3 container actions showed here. One is based on the template that GitHub provides for a container action. Now this action is just using a Bash script bundled up in a Docker file. It's a little bit contrived. If you were just going to use Bash, you would likely put that directly in your workflow. However, it shows how you can wrap things up inside a container image. I then also have the Python container that I was showing on the slide. In order to showcase these, I wrote a simple workflow with 3 jobs. The first one is calling that shell-based container action that is a submodule of this repo. You can see here I'm referencing that path. The second one is running a nearly identical copy of that shell-based container action. However, it's referencing a pre-built image. So if we look at the makefile here, rather than image::docker file, it's referencing this public container image, Sid Palace shell container action at a specific version, which will avoid the need to build that image with each execution. In order to build and push that container image, I just have this simple makefile. I'm just running a Docker build and a Docker push to Docker Hub. Now the third job is executing that Python-based container image, also using the Dockerfile approach, so it's going to build it dynamically. But we should see all 3 of these run, and despite their different configurations, basically the same way. So I can go to Actions, Container Actions, Run Workflow. The instance of our shell container where we use that public container image is done after 5 seconds, whereas the one where we had to build the container image first took nearly double that. If I click in here, we can see the culprit, and that's the step where it's having to build that container image rather than just pulling the pre-built one. The behavior other than that, though, is identical. I mentioned the shortcoming of needing to use these magic strings to interact with GitHub and do things like print out that notice message. The name for this within GitHub Actions is workflow command. There's specific formatting of these magic strings that enable you to communicate with the GitHub Action runner. In general, a string starting with :colon and then a specific word has meaning according to this listing on the right. Within a JavaScript or TypeScript action, we leverage that core NPM package to utilize these. So core.error, missing semicolon, is equivalent to echoing : error, space, and then a bunch of comma-separated key value pairs will behave the same. But as you can imagine, the JavaScript version is a bit easier to read and maintain. These will both result in that annotation shown down below, where you get an error specifically for the file and line specified. As you can see on the right, there's a number of different commands that you can utilize, some of which use those magic strings, other of which, like setting the output, you have to use via that GitHub output environment variable. As you author an action, the ability to control the workflow's behavior in this way can be very important to do things like raise errors or modify the runner state as the workflow progresses. This module speed ran a ton of different ways for which you can write and configure the logic within the steps of your GitHub Actions workflows. I wanted to provide a little bit of a framework for how I think about when to use each of these different tools. I start with the question, was I able to find a public action, a reputable public action in that marketplace that does exactly what I want? If the answer is yes, I'm going to go with that. If the answer is no, now I have to think about how to handle that logic myself. If it's simple enough, maybe a single Unix command or a couple strung together with some pipes, then I maybe just put it in the workflow as an inline shell script. If the answer is no, and I start to need a little bit more logic, then I start to think about, is Bash still the right language to handle this, or do I need more expressivity with a different, more general purpose programming language? If I don't need that additional expressivity and Bash is the right tool, I'll usually pull that logic out of the YAML file into something like a make file or a task file, essentially a task runner where I can store snippets of logic that I want to reuse across different workflows. This makes it much easier to work with and debug. In the developer experience section, I'll show you how I do this. But if I conclude that Bash is not the right tool for the job, I start to have nested for loops and lots of conditionals, then I move down that next branch over to the left, and I start to think about, does the task which I'm trying to accomplish require external dependencies, so third-party packages that I'm going to pull in that are not part of the standard library of a particular language. If I don't need additional dependencies, maybe I just put an in-repo Python script that I call out to from my workflow. However, if I do need additional dependencies, now I'm starting to think about, oh, I need to have a packaging step where I can pull those dependencies in and get them into the runtime environment. Now it becomes a choice of whether I want to use a JavaScript TypeScript action or a container-based action. As I showed, the JavaScript and TypeScript actions have a little bit better support, I would say, on the GitHub Action side. You get that official NPM package for executing the workflow commands. There's going to be many more examples out there in the wild of people utilizing this approach. But if you really have a strong conviction that you want to use a particular language, that's going to drive you down that path of using a container-based action. I often find that most of the time you can get quite far by using a combination of those marketplace actions for things where they exist, and then keeping most of your logic in Bash, but outside of the workflow files. So in Bash, but maybe in a task file or whatever build tool of your choice is. Eventually, you may reach a point where a particular use case requires much more complex interactions. That's where you finally move into a fully featured action that you're going to build and maintain as a dedicated piece of software. The final pieces to cover about actions are how we publish these to the marketplace and how we can consume actions without publishing. Publishing actions is super simple. Effectively, if you have a public repo containing an action.yaml at the top level, then when you go to the GitHub release UI, there's going to be an option to publish it to the marketplace. So for example, if I go to my TypeScript action repo here, I get a pop-up saying I can publish this action to the GitHub Action Marketplace. If I draft a release, it's going to give me a checklist of, do I have all the metadata that is required within my action.yaml? Do I have a README? What category would I want to put this in, etc. So this is just like making a normal GitHub release, but I get this additional information here because it has detected my action.yaml at the root of the repository. The flip side of that coin is if you are within an organization that builds closed source software, you likely won't want to publish your action, but you may want to consume it from a different repo. If your action source code is within the same repo as the one where your workflow lives, you can use it without any additional configuration. You just need to make sure you run the checkout action first. However, for a private repo, you must navigate to the place where your source repo is defined under Settings, Actions, Access, and explicitly allow other repos in the same org to utilize it. It's important to note this only works if the source and the consumer are both private. You can't consume an action defined in a private repo from a repo which is public. Once you've set up access in this way, you can reference the private repo in the same way that you would a public one, as shown on the right there in the middle, where I have a repo named private repo with GitHub Action source, the path to the action within that repo, and then my git commit hash. To test this, I created these two private repos. This first one contains the source for my action. It's just a composite action that echoes hello world. And then on my consumer side, within the settings for this repo, if I go under Actions, General, Access here at the bottom, I toggled this to be accessible from other repos owned by me. Then within my consumer, I've defined my workflow, which references that private repo. I can go to Actions, consume action from private repo, run workflow, and trigger it. It was able to run successfully, despite my source repo being private. Now that we have an understanding of all the different features that GitHub's Action provides, let's go through some common workflows that you might implement for a project you're working on. Now, I showed the same list earlier. I'm going to walk through each of these different use cases and talk through what a basic implementation might look like, which would provide a starting point for you to then go off and implement. If we start with something like linting, a naive approach might be to have one step which checks out our code, one step which installs the linting tool of choice, and then a third step which executes that linter. How can we improve this workflow? We can start to optimize it by adding a step to determine which files will change, and then only running the linter on those files. We also could improve this by reporting the status back on the workflow itself, or if we were running this against a PR, maybe as a status or comment associated with that pull request. Now, we could go off and implement all this ourselves. However, we can actually leverage a marketplace action to handle almost all of this for us. I mentioned this at one point earlier in the course, but there's a tool called the super linter and an associated GitHub action, which handles all of these last four steps, allowing us to achieve linting across a variety of languages in an optimized fashion with just a few lines of code. Here's the marketplace page for that super linter action. If we scroll down, we can see there's lots of configuration that you can do. However, in its most basic form, you simply check out the code, and because it's going to perform that optimization step of deciding which files have changed, we use fetch step 0 to ensure the full history of commits is checked out. And then we can run the super linter action, passing it a GitHub token to enable it to set those GitHub Action status checks that will show up on the PR. And just like that, with those 4 lines of code, we've now added linting across a variety of languages to our project. Now, what about testing? A naive approach to this might be to check out the code, install whatever language toolchain we're using, download third-party dependencies for our application, build the application, and then run our tests. Seems pretty straightforward. However, we can optimize this quite a bit. We want to set up caching and restore from that cache if we have a hit. We may want to upload our test results as an artifact to refer back to in the future. And we'd like to report our status back associated with that workflow. Again, we could implement all this ourselves, or we can leverage public marketplace actions to do a lot of this for us. For example, the official setup node action is going to handle installing the language toolchain, as well as setting up and storing our dependencies from the cache. Now, for the remainder of these workflows, I'm not going to show the optimization for each one. I'll leave that as an exercise for the viewer. However, I'll talk through what I would think is a baseline naive implementation that then you can think about how to extend and improve upon moving forward. Like with linting, for any type of static analysis, generally we're going to need the code, so we'll check it out. We'll need to install whatever tool we're going to run, and then we'd like to run that analysis tool. For building our code base, it looks similar to testing, where we need to check out the code, install our language toolchain, download any third-party dependencies, build the application, and then publish that built executable to whatever registry we plan to use. For a container image, rather than installing our language toolchain, we're actually going to configure Docker or a container builder of our choice to then build that container image and push it to some registry. If we think about deploying our code, this is generally going to start from the end of that build step. So we've already built our application, either as some binary or maybe a container image. We then want to trigger a workflow to deploy our code. One option is to use a push-based deploy from a workflow. In this case, we're going to check out our code to get whatever deployment configurations we need that live there. We'll install some tooling, perhaps kubectl or Helm if we're deploying into Kubernetes, or perhaps the AWS CLI if we're deploying directly into an AWS service. We'll need to authenticate to the deployment environment. If we're deploying into AWS, we can use that OIDC type workflow, or we may need to use a static credential. And finally, we'll want to validate the deployment is behaving as expected. The other type of deployment that is quite common these days is to use a GitOps approach. And so in this case, rather than authenticating and deploying directly into some environment, instead, we're going to modify some configuration that lives in Git and allow an agent running in the cluster to handle the deploy step. Again, this type of workflow would be kicked off at the end of some sort of build step. We want to check out the necessary configurations, update the version references in the Git repo where the deployment manifests live, commit those changes to the repo, and then from there, we'll allow the GitOps agent living in our deployment environment to take over and pull those changes in. Moving on to the repo automations category, if we think about how we might want to automate releases within our repository, there's a variety of things we'll need to do. First, we need to check out the code. Then we need to determine what changed between this commit and the last. Then we need to determine what type of update it is, whether it's a major, minor, or patch version. Oftentimes, I'll use a git commit convention called conventional commits, where you prefix your commit messages with either chore or bug or fix or feat. And you can use that to then determine whether any particular code change represents a major, minor, or patch version when releasing. Once you've determined the new versions, you'll want to update any references within your code base. So for example, within your package.json, you might store a copy of your version, or you might need to update the changelog. And then finally, you'll want to commit those changes back to the repo. In the Capstone project, I'm going to use a tool and an associated action called release please to do exactly this. Another common repo automation is to determine if there are any stale issues or PRs on the repo. And so for this, you would want to retrieve all the issues and PRs, check if any are stale. If they are, mark them as such, and then finally, close any that have been stale for too long. This is another one where there's a public marketplace action that can handle almost all of this very quickly, and we'll do so in the Capstone project. The last one that I'll highlight here is upgrading dependencies. So there's a variety of reasons you may update dependencies. One, there's new features released that you want to take advantage of, but oftentimes you'll need to update in order to handle security vulnerabilities that have been released and then patched within these code bases. To achieve this, generally you would need to check out your code, check against your dependency file, so maybe the package.lock file, to see if the package manager of choice has new versions available. You would then update the necessary references, commit those changes to a branch, and then create a PR. At that point, your test workflow is likely going to kick off and validate that those version upgrades don't break anything across your test suite. Hopefully this quick run through of these types of workflows gives you a starting point for the types of things that you'll want to build and how to approach them and break them down into a GitHub Action workflow. It's often useful to sort of start with a basic naive approach and then think about, hey, how can I optimize this either for performance, user experience, or by leveraging some marketplace action to handle a lot of the functionality for you. It's also useful to show here that under the Actions tab in GitHub, if you click New Workflow, there's a number of baseline workflows that GitHub provides and even suggests potentially relevant ones for your repository based on the code that it finds to use as a starting point or as inspiration for your own workflows. For example, let's take a look at this Docker image workflow provided from GitHub. Here, they're building it whenever you push to the main branch or you create a pull request against that main branch. And so, while this is quite minimal, it is a starting point if you need to build a container image. What if we look at one of these deployment workflows? For example, if we were deploying to Elastic Container Service on AWS, what might we need to do? It provides us a few steps that would need to be performed before this workflow can run. For example, we'd need an ECR repository to store those container images. We would need an ECS task definition that defines how our application is going to be deployed. That would need to be stored within our repository. And we would need to set up the necessary IAM permissions to be able to perform this action. So here we're configuring some metadata about our AWS deployment configuration. And then what steps is it actually going to take? We're checking out our code. We're configuring our credentials. Here they're using a static access key. As I showed in Module 4, it's much better to use the OIDC approach with a temporary token. So I would swap that out if I was going to use this. We're then logging into Elastic Container Registry, building and tagging our image, pushing it to ECR, and then storing that as an output. At this point, we've built our container image, and we shift into starting to deploy it. We're providing the specific information about this particular deploy, which is going to render out an appropriate task definition that we can then use to actually deploy. So in this case, we're leveraging a number of actions that AWS provides to enable a streamlined workflow of deploying into Elastic Container Service. So while there are some tweaks that I would make, like changing how we're authenticating to AWS, and I might tweak how this is being built, perhaps using namespaces, remote builders, but overall, this gives us a strong starting point for a workflow where we're building and deploying into ECS. Here's a workflow handling stale issues and PRs, like I mentioned. In this case, we're using that cron schedule, so we're going to run it daily. And the only thing required is a single step using that stale action, passing it the necessary credentials, and configuring the various labels and messages that we want it to use. We could then customize these to meet our own needs, and then we would have this automation which could run daily and help keep our repo tidy. So my goal with this module was to give you the ability to take a particular task that you need to achieve and break it down into its requisite steps and see how that would map onto a GitHub Action workflow, and then how you might iterate and improve on those workflows to optimize them. It's useful to be able to do that both from scratch as well as search from the template workflows that GitHub provides to use as a starting point. One of the biggest complaints that I have and that I hear other developers have with GitHub Actions is the developer experience for iterating on workflows and actions. In this module, I'm going to show you how I approach this and some tools and techniques to make this a little less painful. Everyone who's worked with GitHub Actions or pretty much any CI system has experienced this pain where a workflow breaks, you try to make a change to fix it, you push that change to validate it, and you get in this cycle of making a small tweak, pushing it, seeing it fail. Each of those iteration cycles is frustrating and takes a significant amount of time. Using the techniques that I'm going to show you here, we can help speed up that iteration process and avoid the number of failed attempts where we actually need to push to GitHub. There's a few different categories of developer experience that I'll touch on here. The first one is going to be iterating on actions. So earlier in the course, we looked at how to build our own custom actions. There's some tooling that GitHub provides to run that action locally. And then also we can write unit tests just like for any other software project. This allows us to validate behaviors of the action as well as execute it in a similar environment to what will be used within a workflow rather than needing to push changes every time to check if they work or not. On the workflow side, and this is where I think most of us are going to spend a majority of the time when working with GitHub Actions, we want to do a number of things. First, we want to make sure that our development environment has the appropriate tooling. If you were following along early in the course, we've already installed the GitHub Actions extension and the YAML extension. There's one more extension here that I use that applies colors based on the indentation level to make it easier to see how your YAML is structured that I'll suggest and show you. But then I also like to do things like pull logic out of inline bash scripts. So rather than define all of my logic in those YAML files, I'll pull it out into a task file and call that from within my workflow. This allows me to iterate on those pieces of logic independently of GitHub Actions. Beyond that, there's a tool called Act, which allows you to run your entire workflow locally within containers. And once you have that set up, it's quite easy to make a change and test it. If you're modifying the git state of the repo itself, those can be hard to test locally. But for most things, for many types of workflows, it's not too hard to configure Act to run them locally. Then, rather than needing to push a commit and wait for a runner to pick it up to execute it, you can make a change and run it locally immediately. There's a couple of other debugging steps that if you do encounter failures and want to understand them, you can perform. There's mechanisms you can use to get an SSH session into the runner itself. That will allow you to check the state of the file system, see whether some executable that you're trying to use is installed or configured improperly, and generally figure out what you need to do to fix things. Now, there's also two additional configurations that GitHub Actions provides that allow us to get additional debug information out. One one, we can turn on step debugging by setting that variable or secret within the repo to true. This will make any debug logs defined within the action appear within the logs of the run. Or we can turn on runner debugging, where we'll get a lot of debug information from the runner itself that normally wouldn't be shown. I'd say 5 is generally more useful than 6. And depending whether the author of the action has provided additional debug info, it can provide insights into what actually went wrong. I haven't encountered too many cases where something at the runner level is causing issues, but if you did need to debug something at that level, setting that variable would be one way to do it. Now, the third category of developer experience that I'll touch on is around optimizing performance of our workflows such that workflow execution doesn't become a bottleneck in your team's process. We want to be able to look at the timing and resource usage data, so things like memory and CPU, and I'll show a couple of different ways that we can do that. Let's jump to my code editor and I'll walk through some of these techniques and how you can apply them. So under module 8, I have 2 subdirectories. There's an action subdirectory and a workflow subdirectory. First, we're going to take a look at iterating on an action. My task file here contains 2 tasks. The first one is to use that GitHub local action tool to run my action locally. And the second one is to execute the tests within my action as defined. You can see I'm pointing it to the TypeScript action that I showed earlier. And so let's click into that and see what's going on. Navigating to that action, module 6, JavaScript actions, TypeScript with build. If we look within the package JSON for this project, there's this local action script, which is going to use npx to call the GitHub local action package from the root of this action directory using our main.ts file as the entry point and passing that .env file, which is where we can provide things like our inputs. If I click into my .env file, here I have input underscore milliseconds. In this case, I'm taking the name of my input, which is lowercase milliseconds, prefixing it with that all caps input underscore, and then capitalizing my input name. So in this case, 2400 milliseconds will be my input. Now I can go ahead and run this by doing task, TypeScript, action, run local action. Under the hood, it's running that npm run local action script. We can see that we should have milliseconds as an input and time as an output. On this line, it shows that it did pick up that 2400 milliseconds rather than using the default of 1000. It ran successfully and then set the output time, which we get logged at the end. So this provides a mechanism for me to test my action with various inputs and see its behavior in a GitHub Actions-like environment without needing to push and have it execute remotely. The other thing that you can be doing when developing and iterating on actions is writing unit tests. This action is a Node.js project. It's using Jest for its testing framework. Within this _test _ directory, there's 2 test files defined. We have a main test that's going to validate that in the normal case, a time output is going to be set, and that in the case where you provide an invalid input, it will reject it. We also have a wait test, which checks that the wait duration is a valid number and that the action does indeed wait for at least as long as the specified amount. To run these, I can run task, TypeScript action task. Under the hood, it's going to run the npm run test script. We can see it identified my 2 test files, ran all 4 tests, and showed that they all passed. If there's behavior that you want to verify is working within your action, you can do so via testing in this fashion. Now let's move on to iterating on workflows. I'll navigate to the workflows directory, where I have another task file defined. The first step is going to be to set up your code editor with the appropriate configurations. In module 3, we set up the official GitHub Actions extension, as well as the Red Hat YAML extension, which helps us with auto formatting. One additional extension that I like is the rainbow indent extension. As you can see here, each indentation level shows a different color. It makes it much easier to tell if my indentation is correct or off as I'm working on YAML files. To install that, you can just search rainbow indent, and the one that I have installed is this top one. The first technique that I like to use is to pull logic out of the workflow file into a separate location within my repo. This way, rather than needing to push a change and execute it, I can iterate much more quickly on my local system. So this first job shows what not to do. So here I have an inline bash script with a hello world. For something trivial, like an echo command, it's fine to have that as inline bash, I would say. But as soon as you move into something a little bit more complex where you're less sure that a change is going to behave the way you want it to, I prefer to move that out. So rather than have a command within my YAML, instead, I'm going to pull that out into, for example, a task file. So here I have a task file. It's doing pretty much the same thing. It just says hello from a task file called from a GitHub Action workflow. And now within my workflow, I'm going to call out to this task. So in this case, I check out the code so it's available. I install task because it's not available by default on our runners. And then I'm able to execute task hello world task. For something like echoing hello world, this may seem like additional unnecessary work. Being able to come here and just say task hello world task. Okay, what if I wanted to say something different? Called from GitHub Actions. And now I was just able to make a change and validate that change within a couple of seconds, rather than needing to make a commit, push to GitHub, wait a few seconds for that job to get picked up, and see that it worked correctly. So tightening that iteration loop is really what we're trying to do here. Also, steps like this, installing task, I'm oftentimes going to pull those into a composite action that gets shared across all of my different workflows because it's such a common thing that I use everywhere. I won't end up with this snippet bloating all of my workflows. I'll have a single snippet called install dependencies, which will handle this for me. This approach works great for testing some small, distinct chunk of logic. However, what if you want to test your workflow as a whole? That's where the Act project comes in. So the Act project comes from the Nectos organization, and it allows you to take your actions and run them in a series of containers using a local container runtime like Docker, such that we can, in many cases, approximate a remote runner with enough fidelity that we can validate workflows locally. So how's this going to work? If you're using DevBox, you should already have Act installed. So I'll create a DevBox shell. And you can see I have version 0279 installed. Now I need to write a command to reference my specific workflow. That's what I have here. So I'm going to use Act, and then you use the name of the trigger. So in this case, the workflow that I want to utilize is workflow dispatch. I'll use this a bunch during the Capstone project. I can even go as far as creating a JSON file containing all of the metadata I want associated with this trigger event to handle all the different conditions which may occur when triggering a real workflow. In this case, I'm not passing additional inputs or anything, so just using the workflow dispatch type is enough. Because I'm on a MacBook running Apple Silicon, I'm telling it to use the AMD 64 variant of any containers that it pulls. The -p option allows us to specify which container image we want to use as the runner. And this will swap out the Ubuntu 24.04 that I have defined in my workflow file with the container image and tag defined here. Now in this case, the Node.js is a sufficient replacement, but depending on what your workflow is doing, you may need a container image which is more representative of the one that GitHub uses. If we look in the Act documentation, you can see they've provided here a micro, medium, and large image that approximates each of these runner types. If your workflow doesn't depend on many things that are installed or configured on that runner, the micro image is likely sufficient. If you do end up relying on a particular configuration in that runner, you may need to move to the medium or maybe the large Docker image that much more closely matches the set of installed dependencies. However, these images are quite large, multi-gigabytes, and so sticking with one of the smaller images can avoid needing to pull these large images before you can run. Here I'm telling it which directory to use as my starting working directory. I generally set this to be the root of my project. This way, relative paths within the workflow will behave the same as from when you execute in the remote runners. And then finally, I'm passing it specifically which file I want to execute. If I omitted line 12, it would trigger all of the workflows using a workflow dispatch. So this allows me to limit it to the specific one that I'm testing right now. Now running this, it identified my Docker runtime. You can see the two different jobs within my workflow are prefixed with their name and have different colors. This is executing both the say hello inline bash job as well as the say hello external task job. You see lots of setup. It does end up being a bit noisy with all of these logs interspliced. However, if we scroll down, we see the output expected from the inline bash script. And then similarly, we see the output expected from the task file task. Unless otherwise specified, it does use the local copy of your code base. When performing the checkout action, it mounts that into the container rather than checking out from GitHub. And so it will pick up the latest changes. For example, if I modify this to append in Act to the end, and I run it again, now we got that new message populated from within my workflow run. Again, the goal here is to shorten the iteration time for any change such that we can make changes and test them as quickly as possible. So step 1, pull the logic out of your workflow file itself and test individual chunks. Step 2, run the whole workflow, but run it locally. Once we're confident that things are working, now we can make a commit and push that to GitHub and avoid that dreaded string of failures in our Actions tab. Now, what if things still aren't working and you can't figure out why locally? One step that you can take is to set up access to that runner environment via SSH using something like this breakpoint action from Namespace. So here I have a simple workflow, which is going to do 3 things. It's going to check out my code base. It's going to purposefully fail. So it's going to run this echo and then exit 1. And then I have this step, which is conditional on failure. So it's only going to run in the case that an upstream step failed. And it's going to run this breakpoint action from Namespace. I'm providing it a duration for how long it should keep this step open. And then also a set of authorized users that are going to be able to utilize it. Let me go ahead and run this. I've named this workflow breakpoint with SSH. I'll trigger it. Okay, our first step ran, it checked out the code. This step purposefully failed. And because of that failure, it ran this conditional step, which is going to give us a connection string that we can copy. We have to accept the fingerprint. And now we have a shell session directly within that runner environment. So we can see the code that's been checked out. Let's go into developer experience. Under workflows, we've got our latest task file. And let's say I was attempting to execute this from within the runner. I could say task, hello world task. And look, it's saying, oh, task is not installed. That's because in this workflow, I haven't installed it. I can then go back and rework my workflow to handle the bug that I just found. You'll also notice that when we first connected, it gave me two options. I could either extend the duration. So right now I had it set for 10 minutes, but if I needed additional time, I could do breakpoint extend. Or if I was all done, I can issue the breakpoint resume. That'll terminate my conditional step and allow the job to go ahead and finish. This approach is nice because this only runs if you have a failure. It works across GitHub hosted runners as well as third-party runners like Namespace runners seamlessly. There's a couple of other debugging features that GitHub Actions provides, and we can take a look at those with this simple workflow. It's just a single job with a single step that echoes something at the debug level, something at the info level, and something at the warning level. First, I'll just run this. So this is going to be the default behavior. Now we shouldn't see that debug log, but we should see the others. So here we've got info and warning. But let's say something was going wrong and we wanted to see the debug logs from the author of whatever action we were running. In order to do that, we can set an environment variable here. We can go to secrets and variables, actions, and set the action step debug variable to true. You could also set this as a secret, and I believe that the secret would override the variable if both were set. Let's go ahead and rerun our action. I'll go ahead and just rerun all jobs. Now, because I've added that action step debug, I'm getting these additional debug logs, including the debug that I specified here. And then similarly, I can add the actions runner debug variable. So I'm actually going to delete this one and add this one. Rerun one more time. You'll also notice that when rerunning a job, you can trigger this without needing to modify those variables directly. Now that we've enabled that as true, we can click here, click Download Log Archive, opening up the zip file that was provided. These are the step logs, but we also get some runner diagnostic logs now. Tons of info from the runner itself. Now, like I said, generally I haven't encountered too many issues where something this deep in the runner layer is impacting my workflow behavior, but it's useful to be aware that you can get access to these if you need to. Now, the final piece of the developer experience puzzle that I wanted to touch on is understanding workflow execution, timing, and performance. The default user experience here is somewhat poor. You can filter down to a particular workflow and then sort of try to eyeball the different timings and say, okay, it looks like over time this is trending upwards or trending downwards. That's not a great experience. There's a couple of ways you can get these data out. In fact, in the past, I've written a custom action that would run daily and it would pull timing data. There's two approaches that I use that I think are more useful than that. The first one is many of these third-party runner hosting companies provide some sort of insights or analytics out of the box. So if I go to my Namespace account, under Insights, I can now filter down to a particular job and showcase, let's say the last 60 days, all the different timings for that job. You can also see the CPU usage within that job or the memory usage within that job. And this will help you understand whether resource constraints are causing your workflow to run slower than expected. This is great at the job level. However, it doesn't give you insights at the step level. For that, I generally export the timing data from my workflows into Honeycomb. Honeycomb is an observability platform that is generally used for doing things like tracing of your application code. However, I found this marketplace action, which is able to query the GitHub API and turn the timing data for workflows into the same format that would be used for normal application tracing. It then ships those off to Honeycomb, at which point I'm able to view timing data at not just the job level, but the step level and set up dashboards, etc., to track those over time. This is from the Capstone Project. I'm saying for these workflows, whenever they finish, go ahead and export those data to Honeycomb. For my usage, this fits well within the Honeycomb free tier. Let's go take a look at what happens. I can filter by a particular workflow. And now because this is a demo project for the course and doesn't have a team of developers making changes every single day, the history here is a bit less useful, but you could imagine something like this over time where you're seeing how long each of these, and this span maps onto a step within a GitHub Action workflow. I can start to see trends over time, but I can also click into an individual workflow run and see each portion of it broken down. So this total workflow took 1 minute and 4 seconds. You can see we spent 7 seconds queuing, 5 seconds within my filtering job. So this is sort of determining which services need to be built. And then for each of my services, I can see how long each one took to build. So in this case, there were 2 container images built. The first one contains my migration scripts. That one took 20 seconds to build. The second one took 47 seconds. And I can see down at the very granular level where this time is being spent. And so it's hugely valuable to take those timing data and get them out of GitHub Actions into a platform where you can track over time and really dive deep to investigate where potential inefficiencies may lie. At this point, we've seen how to author GitHub Action workflows, how to write GitHub Actions, how to improve the developer experience. Now I want to talk about some best practices for using GitHub Actions within your projects. And then we're going to try to apply a number of these best practices as we move on to Module 10 and build out the Capstone project for the course. There's a few different categories of best practices. The first one that I'll touch on is performance. There's a number of performance-related aspects that we can optimize within our GitHub Action workflows. First thing we want to do before anything else is to measure the performance. It doesn't make any sense to try and optimize something if there's no way for you to tell if that optimization actually improved the state of things. A good way to measure this is to export those timing data to some third-party platform that you can use to analyze the data and see what is taking the most time, which will inform your decisions about where to invest your efforts. The next thing I would suggest is to figure out how to spend less time waiting. And so this could be in runner queuing, so waiting for a job to be picked up by a runner, or ensuring that the types of tests that you're executing, which may frequently fail, can do so quickly and inform developers so that you can fix it and move on much more quickly rather than running for a significant amount of time before eventually failing right at the end. So ordering the tests that you do within your workflows in this way can avoid wasted time. The third approach is to try and do less. And so by this, I mean, don't execute things unless they are actually necessary. You can use conditional filters to only run workflows, jobs, or steps when the relevant code changes within the repository. And you can use caching to avoid repeating work that was done in a previous execution. Fourth category is to improve our resource utilization. This could mean splitting work across jobs so that they can run in parallel, splitting work within a job so that it can run across the multiple cores that your runner may have, and also avoiding emulation where possible. QEMU is an emulation technology that allows you to build applications for a different architecture than you're running on. So I can be on an ARM64 system and build an AMD64 executable or vice versa. However, it does incur a large performance hit. And so where possible, building for the same architecture that you're running on will be much more efficient. This is often how many of the remote container building services achieve such dramatic speedups, is by skipping this emulation step and instead splitting the work for the builds across multiple different runners, one using each architecture, and then stitching those images back together into a single multi-architecture image. The fifth category is once you've done this and you've started to optimize your workflows, make sure to keep track of those timings as development progresses to avoid the inevitable slowdown as you add more code, more tests, etc. You want to keep an eye on these things and flag them before they become a bottleneck for the team so that you can keep development velocity as high as possible. Diving specifically into caching as a performance improving mechanism, there's a number of different types of things that you may want to cache depending on your project. One is Git checkout. If your repo is quite large, it can be helpful to have a cache with a reasonably recent copy of your repo so that each new workflow run only needs to pull in the delta when it performs the checkout action. It can also be useful to cache the language toolchain that you're using. So the runner has many toolchains installed out of the box, but if you're using a different version than the one that is installed, you may need to install and configure it yourself, and caching that across runs can avoid needing to download and configure it each time. Dependency downloads are another key category where caching is a big win. Rather than pulling from your package manager with each build, you're able to store a copy of those dependencies in a cache. It can be accessed much more quickly than needing to pull over the public internet. Build and test artifacts are another thing that you may want to look into caching, depending on their size and scale. And then 5, within the category of containers, you can cache images. So if there's a base image that you're using over and over, it's great to have that available in a hot cache. You can cache individual layers such that if nothing about that layer has changed, you're able to reuse that in future builds. And then you can also use what are known as cache mounts, which allow you to take advantage of something like number 3, where you're able to leverage, let's say, an NPM cache from within a Docker build context by mounting in a local volume into the container at build time. The next category of best practices that I'll touch on is maintainability. Not only do we want our workflows to execute quickly and efficiently, we also want them to be maintainable. Depending on whether you have a mono or a multi-repo for your code base, there's going to be a variety of different considerations that you want to take into account. I'll talk about those in a little bit. But one of the most powerful approaches I've seen is to define a standard continuous integration API or a standard service API for every single service that you're building. Pick a single tool that you're going to use as the entry point for each service. In my case, I'm using Task. That could be something like Bazel. It could be a Makefile. I want you to pick a standard approach. And for each of those services, have a standard set of commands such as install, test, build, dev, such that whenever a developer comes to a new project, they know exactly what's going to be available, and they know that running make dev will get them up and running right away. The benefit from a GitHub Actions perspective is now we can have a standardized approach within our workflow to perform our testing, to perform our build, etc. As we talked about in the module focused on building our own actions, we can use composite actions and reusable workflows to avoid duplicating logic. And then as we saw in the developer experience module, you'll want to make sure you set up the tooling appropriately on your local system to ensure that you can iterate quickly and test changes without needing to push them to GitHub and run remotely. I showed both of these flowcharts earlier, but I think they're relevant as we think about maintainability. The left-hand side focuses on reusability of code and whether we should use a standard workflow, a reusable workflow, or a composite action. Depending on your needs there, these can be great tools to take code that would be otherwise copy-pasted across workflows and move them to a centralized location, making making them much easier to maintain. And then on the right-hand side, this focuses on how to perform a particular piece of logic within our workflow, whether we can leverage a public marketplace action, whether it's simple enough to live as inline bash within our YAML file, whether it should move out into a separate task runner, or eventually even into its own custom action. These diagrams give a snapshot of how I approach these various situations. People have very strong opinions about monorepos and multi-repos. I'm not going to make a definitive claim about which of them you should be using. However, I want to sketch out the different considerations you have for each of these two different approaches when it comes to GitHub Actions. In terms of reusing logic, in a monorepo, that is super easy. All of the logic lives within that repo, and it's simple to reference across different workflows. In a multi-repo, it requires some additional setup. You'll likely want to have a separate DevOps utility repo, or maybe a GitHub Actions repo, where all of the shared logic can live, and then you will reference that from your other repos. From a discoverability perspective, having things within one repo makes it very easy to search across the entire code base and see what is available. If you do have a multi-repo setup, you'll need to be a bit more intentional about establishing the types of patterns and documentation such that people can find the available functionality and not end up re-implementing it over and over. From a performance perspective of only running things when they need to be run, this is much harder in a monorepo. Only a small percentage of the PRs or the commits are going to be relevant per particular service. So you need to be very careful with the types of paths filtering or change detection that you're performing to ensure that you're not running a bunch of wasted, unneeded workflows. In a multi-repo, this becomes much easier because the repository boundaries serve as isolation to prevent this. From a caching perspective, again, monorepos are much trickier because you need to scope all of your keys to avoid collisions and ensure that each cache is appropriate for the particular artifact that you're trying to store and retrieve. In a multi-repo setup, you kind of get this out of the box because each cache is going to be isolated based on the repo that it's associated with. From an artifacts perspective, within a given repo, this is quite simple. In terms of handing off between different workflows or storing artifacts within a single repo, this is quite easy. But if you have a multi-repo setup, you'll often need an external registry, either a packages registry or maybe an object store like S3, or use GitHub releases themselves to perform that type of handoff. For managing permissions and secrets, a monorepo is easier to work with, but harder to give you the level of granular control that you might want across different permission levels and environments. In terms of setting up required checks or policies, these are generally going to be applied at the branch level on, let's say, a pull request. It can be much harder to get the level of granularity that you might want. In the multi-repo setting, it's easier to configure, but it requires configuring each repo independently and has the possibility for drift, where if you want to make a change to one of these checks, you need to then go off and apply it to all the different repos. In terms of the scale of these things, within a monorepo, a large pull request may fan out tons and tons of workflows, and so there could be contention for available runners if you're not careful. Dependency updates can be quite nice for a monorepo because you can atomically update all the services and pipelines in one single PR. Across a multi-repo, it can be quite challenging where you need to find and apply these updates across lots of different PRs. And so you'll likely want some additional tooling to handle that orchestration. And then from an auditing and ownership perspective, a monorepo is easier to audit, but you need to really put the effort into the code owner's file to specify which services belong to which teams. Within a multi-repo, it's often clear who that service belongs to. However, all those configurations are scattered across many different places. And then as we think about best practices from a security perspective, I've mentioned some of these throughout the course, but we want to grant the minimum set of permissions required to do the work that we need to. We want to try to avoid long-lived credentials and use short-lived tokens wherever possible. In terms of consuming public marketplace action, setting up an allow list for specific approved actions is a powerful technique. As we've done throughout the course, you'll want to pin the action versions from the marketplace using the commit hash rather than using a tag, as that's the only way to guarantee you're going to run the same version each time. It's important to not allow self-hosted runners to execute fork PRs. This helps prevent a malicious actor to exfiltrate information about the self-hosted runner by modifying the repo and the actions within it. And then finally, using the environments feature, GitHub has the ability to require approval for running workflows within specific environments. So maybe most environments run automatically, but you have to have an approval from a specified user before you execute workflows against the production environment. Many of these concepts I brought up throughout the course, and we'll start to see them come into play as we build out the workflows for our Capstone project in the next module. Congratulations, we've reached the final module of the course. This one will be a big one. We're going to try to take everything that we've learned throughout the entire course and apply it into a realistic project containing multiple services and build out the types of GitHub Action workflows that you would want as a team working within this code base. If you've taken my Docker course or my Kubernetes course, this application will look quite familiar. It's a minimal 3-tier web application. It has a React front end. There's 2 different API implementations that front end is calling into. One is written in Node, another is written in Go. There's a Python load generator that just repeatedly makes calls to one or the other APIs, and then it's backed by a Postgres database, which tracks each page visit. You can see a screenshot on the right of what the application looks like on the front end, and I've structured this as a monorepo containing the application source code, Kubernetes manifest for us to deploy into a Kubernetes cluster, and we'll be putting the GitHub Action automations there as well. Now I've sketched out the types of workflows that I want to implement here. I have 6 workflows that I'll be implementing. The first one at the top there is a test workflow that's going to run a set of unit tests for each application. The second one has to do with automating the release process based on commits to the repo. The third one is for building and pushing our container images to registries. The fourth one in the middle is identifying and closing stale issues and PRs in the repo. The fifth one is to export timing data from our GitHub Actions into Honeycomb. And then the last one is to update our GitOps manifests automatically when we build new images, such that we can deploy those updates into the different Kubernetes clusters for each environment. Let's jump to the code editor and start building these out. The Capstone project is its own Git repository. It is also a Git submodule of the course repository. I'll caveat with the fact that I did implement this ahead of time such that I would know everything would work as expected. However, I've wiped out all the GitHub Action related code on this branch so that I can start from scratch as we walk along and build this out. Looking within the repo, you can see I have YAML files for each of these, but they currently have no logic and are just a hello world for each of them. Over the next hour or so, we'll be building out these workflows, referring back to everything we've learned from the course to end up with a robust DevOps system ready for a team who is working on a code base like this to utilize. Let's quickly take a look at the application just to familiarize you with all the different components. All of the application code lives under the services subdirectory, which are further split by the language in which they're written. So under Go, we have our Go API. Under Node, we have our Node API. Under Python, we have the load generator. Under React, we have our front end. And under Other, we have our database migrations to establish the schema within that Postgres database. Now, all of these will use that DevBox setup. So I'll do DevBox shell. And the first thing I'll do is start a copy of our database. So I'll go into Services, Other, Migrator. Within here, I have a task file. The task that I want to run is run Postgres. I'll run that run Postgres task, which is going to start a container running the appropriate version of Postgres. Next up, I want to run our initial migrations. So again, I'll do DevBox shell. And now I want to run my Postgres init script. It ran the SQL script, which created my request table. In that request table, we have a created at field, as well as an API name, which will specify whether the Node API or the Golang API sent the request. We can now navigate to one of those API layers. So under Services, Node, API Node, we have a task called install that I can use to install my NPM dependencies. And then we have a task called run that I can use to run the API. So I'll do t install. Followed by t run. And now this API should be listening on localhost port 3000. Now the Node API is running, and each time I request, that number should go up. Once again, we'll start a DevBox shell in a new terminal. We'll navigate to our Golang API. I'll first install my dependencies, which calls go mod tidy under the hood. And then I'll run. As you can see, I've got this standard interface for each of these services where I run task install, followed by task run, and now I'm up and running. This should now be listening on localhost port 8000. And we can see, here's our Go API. You'll notice the request count is a little high. This is because I am storing the data from that Postgres database in a volume. So those data were not deleted the last time I ran this application. With each new request, that count goes up by 1. And we get these logs to the terminal. We'll create our DevBox shell. Our Python load generator has the same interface. We'll do task install, followed by task run. And now we're making lots of requests to localhost 8000, and we can see the Golang API is receiving those requests. If we go back to our browser and refresh here, we'll see that number is now climbing much more rapidly as the load generator continues to make requests in the background. Now finally, let's spin up our React front end. We'll navigate to the React client React subdirectory, and DevBox shell, run task install, followed by task run. And now we can open up in the browser our application. With each refresh, we're going to make a request to each one. But as you'll notice, the Golang API is what the Python load generator is hitting, so that's going to climb much more quickly. So we refresh once, we get one additional request on the Node API. However, a bunch of requests have been made in the background on the Go API. I won't look at the source code for each of these applications. You're welcome to do so. They're quite minimal, but I wanted to show you how all the pieces fit together and demonstrate that shared API across all the different services. That's going to become important as we try to design workflows that can be reused across the entire repo. You may also be wondering why I structured it in this way, with each service living under a subdirectory of its language. It's because in my GitHub Action workflows, I'm going to make sure that the appropriate language toolchain for each project is set up based on where it lives in the repo. And so by doing some careful planning ahead of time about how I structured this, it will greatly simplify the logic required to ensure that the appropriate tools are installed. I'm going to go ahead and stop this application. And we can talk through how we're going to go about implementing some of these things. As you saw, this project and all of the services live within a single repo, so you'll want to think back to some of those considerations I mentioned before about monorepo versus multi-repo. In this case, we'll want to be very careful about how we decide what to execute within our CI pipelines, because I may be making a PR against one of these services and don't necessarily want to run or impact tests and code across all the others. That's what this filter step here in the test and build push workflows represents. I'm going to check which services are relevant for any particular code change and use that to dynamically generate the set of tests and builds that are run. Then I'm going to leverage the matrix strategy that we saw before to take that set of tests or builds and spawn a set of jobs that run in parallel to execute them. Now let's start with that test workflow. Back in our common workflows module, we sketched out this test workflow. So let's follow something like this. We're going to check out the code. We want to make sure we have the correct version of our language toolchain installed. We'll download any application dependencies, build our application, and then run the tests. As shown at the bottom there, we're going to leverage public marketplace actions to handle things like toolchain setup and caching. For now, let's have a single job within our workflow called test. We'll run on the latest Ubuntu, and we'll start by checking out our code. Let's find the latest version available. Here's the official Git checkout action. The latest release was version 5.0. Actions checkout at that 5.0.0. Once we have the code checked out, we want to install our language toolchain. As a starting point, let's design this workflow for just one of our services. Let's use the Node API. For this, we can use the official Node.js action on version 5.0.0, but let's go ahead and find the associated commit. Go here to view source code, find that release, copy our Git hash. I'll add a comment to ensure that we set up the correct version and caching, but we can continue on. Now, just like we had our install and run tasks, we also have a test task. So I go here under my task file. We can see that test is going to run npm run test for the Node project. For Go, it's going to run go test, etc. For each of our services, we have the standardized test task that we'll call into from our workflow. However, task is not installed out of the box on these runners, so we're going to need to install that as well. If we look at the marketplace and search for task, there are a couple of different options here in the public marketplace that you could use to install task and configure the GitHub path accordingly. The way that I like to do this is using an action called setup binary, which can be used for any executable binary, but you provide it a path to where that release lives, the name of the binary, and the version. This will follow all the standard GitHub Action conventions for installing things within the toolchain cache. Now I need to give it a path to the release that we care about. To find that, I can go to the task GitHub, find the latest release, look for the Linux AMD 64 version, copy that address. This will be named task, and the version here is v3.44.1. With our code checked out, Node.js installed, and task installed, we can now first run our install task and then our test task. Within our task file, this was the install command we ran locally. However, in CI, you generally want to run the npm CI command. So we have a separate task that we'll use from within our CI workflows. And we also need to specify the working directory for this step. And that's going to be from the root of the repo, services, node, API node. And lastly, we'll want to actually run same working directory. And here, this will be just task. Now I could push this to GitHub and run it there, But as I mentioned, we want to set things up properly locally so that we can iterate as quickly as possible. The general idea here is we're going to use act and configure command to run this workflow locally to allow us to validate it before we push anything to GitHub. I'm going to create a subdirectory here called test, matching the name of the YAML file. Within that, I'll have a task file using version 3 of the task file syntax. My set of tasks will include trigger workflow. This is going to trigger my workflow using act. The command I want to run is going to be act workflow dispatch. I'm going to specify my container architecture as Linux AMD 64. By default, it would use the architecture of my MacBook. In this case, I want to match the architecture of my runners. I'll specify which container image I should use instead of that Ubuntu 24.04 image. Now, in its current setup, the slim node image probably would work, but I know eventually I'm going to be using some Git operations. And so having Git available in the runner is going to be necessary. So I'm going to go ahead and use this larger act image now because I know it has all the dependencies that are going to be needed down the road. I'm going to specify my directory where this should be executed from. And because I'm within .github workflow test, I'm specifying 3 steps up to run this from the root of the repo. And then finally, I'll pass it the path to the workflow that I actually want to execute. Now let's try and run this. So I can navigate to .github workflows test. I'll run task trigger workflow. First, it's going to pull that image specified to use. And so this is interesting. Within the setup node action, the latest version is using node 24. I believe that was just updated recently. So if I go to this repo, view source code, the action.yaml file, we can see it's using node 24. Let's look at when that was updated. Yeah, just last week. And so they've just updated the runtime. However, act is validating the runtimes that it thinks are available, and the version of act that I'm running hasn't updated to include node 24 in that list. While I think this has been updated in the act repository, because I'm using DevBox, I would need the latest version available via Nix to also be updated. Rather than try and fix all that, I'm going to use one version earlier of the setup node action, which will be running on node 20 and should be allowable. That'll be version 4.4.0. So I'll modify this to reference that. And now let's try running it again. Looks like we also hit the same issue with the setup binary action, which was just updated. Let's find one prior release. So we'll downgrade it to the v4.0.1. Run again. Right, it looks like we were able to run successfully through the entire workflow. However, we did get these issues about an unsupported engine. That's because it's running the default version of Node on the runner rather than the version specified in my package.json. So if I go here to my package.json, I've specified my NPM and my Node engines. In this case, I'm saying I want a Node version greater than 20, but less than 21. And in the setup node action, I can actually pass it a path to this, and it will look up the desired engine to utilize. You can pass it a version directly. However, because I already have the engine defined within my package.json, I'd rather reference that file via this input. So I can add with node version file. Here it's going to be services node API node package.json. And similarly, we can set up caching by passing it a path to my package.lock file. So here, I'll do cache dependency path. But instead of my package.json, this will be my package lock.json. And then I also need to tell it that this project is using npm by specifying cache npm. So with these 3 inputs, we're giving it the appropriate version to download and install. We're telling it which type of cache to use, as well as which file to use to determine an appropriate cache key. And now when we run it again, we see that it installed an appropriate version of Node. We no longer get that warning about the incorrect engine. We configure our cache. We install our dependencies. You can ignore these for now. As you can see, I haven't updated my dependencies in a while. Maybe I should do that. And then we ran our tests. Now my test suite here is just a single example test, but the point is that I'm doing all the steps that would be required for a much more sophisticated testing setup. I've got my runtime, I've installed my dependencies, and I'm executing all the tests that are found. Okay, this is great, but it only works for one of my services. How can I apply this across more different services? Let's use our Go API as the next service to incrementally add. I'll also call out that an issue I ran into with Node 24, that would not be an issue when running these remotely with GitHub Actions. That's only an issue I'm encountering locally with Act. Once I'm able to update Act within DevBox to support those, I'll likely update the version used for these different actions. How can we get our Golang tests to work? Now, the simplest approach might be to copy this entire job, call this one test node, call this one test go, and then all we really need to do here is to modify this step to install and configure the Golang toolchain, and then modify the name and the working directory of these to call the corresponding tasks within the Go API subdirectory. Let's go ahead and use this copy-paste approach for now before we refactor it into a more modular approach. So we've got test go. Here, instead of setup node, we're going to look at setup Golang. Here's the setup Go environment. Now, if we look at the releases, looks like they did use this newer node runtime. So let's use the previous one of 5.5. Instead of the node version file, this takes as an input the Go version file. That's going to be services, Go, API Golang. And then instead of package.json, it'll be our go.mod file. In terms of the cache, it is enabled by default. And the file that we care about for determining the cache key is going to be our go.sum file, which is similar to the lock file in NPM. We still need task, so that'll stay the same. Instead of node here, we're installing our app dependencies at the path services Go API Golang, and then we'll run our tests. And so I think with those minor modifications, we should now have two different jobs, one testing our node application, one testing our Go application. The logs from these are interspliced. We've got our yellow prefixed node and our green prefixed Go. Scrolling up, we see our Go tests were executed here. They ran and they passed. So we successfully installed and configured our Go toolchain, built our application, and ran the tests against it. Now let's start to refactor to make this a little more maintainable. We don't want to have to copy and paste this job across every different language configuration that we might want. And instead, we can utilize how we structured the repo along with the matrix feature within GitHub Actions to combine these into a single job that runs with two different configurations. So we'll go up here to our first job. This will be test all, the same runs on, but now we're going to add a strategy. I'm actually going to set fail fast to false. So if it's running the test for one service, it won't cancel the test for the other. So we'll get signal about each of them on whether they're passing or failing, rather than just one if it fails. And then we'll use the matrix strategy. Within the matrix strategy, we're going to specify the service that is being tested. And here we're going to have a list that contains the paths to our two services. So the first one is going to be services API node. And the second one, services Go API Golang. We'll set up node here. We need to set up Go as well. Now the rest of the workflows were identical, so I can remove this. We'll rename that to make it generic, and then we need to extract the working directory from the matrix context. So to do that, we can use our $ curly braces syntax and specify we want the matrix service to be the working directory. Now, I'm not sure if I need this trailing slash here or not. Let's actually take it away. Similarly, for our testing, we'll want to use the matrix service as our working directory. And now there's still one issue here, and that's that for my Go project, I'm not going to have these files available. And for my Node project, I won't have these files available. So let's make these steps conditional based on what the service is. So in this case, I'm only going to set up Node if my matrix value, matrix.service equals single quotes services / node / star. And I'm only going to set up Go if my matrix.service is under the Go subdirectory. Let's see if I got that right. So I think what was happening here is that in this case, both of these conditionals were returning false. So I think it was looking for a literal match of that exact string rather than leveraging this glob pattern. Instead, I'm going to use the starts with function. And in this case, I'm going to say matrix.service starts with services/node. We'll close that. Do the same thing here. Except here it will be services go. Now that we're using the starts with approach, I believe the filter should work properly. Looks like in the go job, we're setting up go. In the node job, we're setting up node. We installed our dependencies, ran our tests, and both of these jobs succeeded. So now we have a single matrix job, which runs for both of our services, conditionally installs necessary dependencies, and executes our tests. Next, we can extend this to work for our React application as well. Our tests for the React client are also in Node.js, but we have a different path here. So I'm going to modify our conditional slightly to add an or condition. So if it starts with node, or if it starts with services React, we want to set up our node environment. And so just by modifying those two things, adding our client React and telling it to install node appropriately, because we've used the conventions of specifying our engine version in our package.json, specifying that task to have task install CI and task test, only those two modifications were required to now run our test job for the React project as well. Let's validate that things are working. So it looks like yellow is our Node API, green is our Go API, and purple is our React client. So let's look down here and validate that our client React ran its just tests, and they passed. So we made those two little tweaks, and now we're running our tests across an entirely new service. Now the final project that we want to execute tests for is our Python load generator. So we're going to add that to our matrix. So it's at path Python load generator Python. We need to add an install step to configure Python and Poetry, which is the package manager that we're using. So we'll look up the official setup Python action. So here's the official Python setup action. Let's find latest releases. We're likely going to hit that same Node 24 issue. So I'm actually going to use this version 5.6, which is commit hash A26A. So it'll be uses the official setup Python at that particular hash. The configurations we need here to set up caching and the appropriate engine version are Python version file. And you'll notice these additional tooltips. These are coming from that GitHub Actions extension. It's looking up the metadata associated with the action and providing me with the available fields that I can specify. The Python version file in this case is going to be services/python/load generator Python/ and because we're using Poetry, it'll be pyproject.toml. This just made me realize that having these hard-coded is a bug, such that, for example, a React client would have used the incorrect inputs here, and these should instead be dynamic using the matrix.service. We also want to configure caching using type Poetry, and we'll specify the cache dependency path as the poetry.lock file. Now, interestingly, the runner does not have Poetry installed out of the box, nor does this install and configure it. Before we can execute this, we'll need to install Poetry. Let's first attempt to run this and see it fail before we add a Poetry setup step. Oh, also, I didn't make this conditional. So we don't want this to run every time. Instead, we only want to run if our service starts with services/Python. I've already added Python to my matrix. I'm going to go ahead and comment these out and just test this for my Python service. As expected, we were unable to locate Poetry, so we're going to add a step prior to doing our setup Python to install the version of Poetry that we want. So we're going to have a step install Poetry. It's going to have the same conditional as the Python install, and then we can search the marketplace for Poetry. This one looks fine. We can take the latest version, going here to the source code and seeing that this release 141. And so we'll specify uses, pointing it at that action, at the commit, and the tag that we want. Now, if we run again, we get past that issue with poetry. We installed our project, downloaded dependencies, and ran our tests. And so at this point, we're looking pretty good. We've defined a workflow in about 50 lines of YAML that can handle setting up the appropriate tool chains and test all of our different services across the code base. However, as defined, it's going to test each of those services with each change. Now we want to think about how we can filter this down so it's only running the test for the services which were modified. There's a couple of approaches we could take. We could have split these into separate workflows and then used conditionals on the trigger. So saying only trigger this if this path changed or that path changed. However, the approach I like is to have an upstream job which does that validation for us, and then pass that into a downstream step such that this matrix will be dynamic at runtime and only contain the services which have changed. An action which I really like for doing this is this path changes filter, which does exactly like I described. It's going to look at the repo and see, based on my branch or pull request, which files within the repo have changed, and then based on my configuration, output a set of services that it should run. Using which files were modified is a specific, somewhat naive implementation of what might more generally be called a determinator within a build system. So something like Bazel is going to have a much more sophisticated approach to determining, based on the inputs to a particular build target, when it needs to be run. And so I'm using this paths filter approach to approximate something like this, and it's fine as long as the assumption that each of my services lives in a subdirectory that is not impacted by any others is valid. So if we look at an example of how this is used, let's go to this example from Sentry.io. Within their backend.yaml file, we're using this action, and it references this file filters YAML file. Let's go to that. Within file filters, we have a whole bunch of different top-level keys defined. These are the different potential outputs of this action, and depending if the files specified in the array under that key have been modified, these will either be included or excluded from the output list. So we'll go here and find the version that we want to use, 3.0.2, commit DE90, and we'll add that to an upstream job. So I'm going to call this job filter. We'll use our same runs on. In the set of steps, it's going to have one step. We'll call it filter with the ID filter. And we need an ID here because we're going to pass an output from this job to the downstream job. We can specify that it uses that action at the desired commit. Then we're going to do two things. One, we need to pass it a token so it can access the GitHub API and appropriately determine what has changed. And two, we're going to pass it the filters key, and we're going to reference a new file that we're going to create just like that one we looked at. I'm going to create a file called filefilters.yaml under GitHub utils. Now within this, I'm going to have a top level key for each of my services. And under that, I want to include all the paths that are associated with this particular service. So in this case, anything under that service directory will be included. And I'm using glob patterns here, so this will capture any file modified in that subdirectory. Now I also have the migrations associated with this service. And so we saw that earlier when we ran our DB migrations. This is where those migrations live. If those change, effectively, our API Golang is changing as well, and I'll want to run the tests and build those. And then finally, I would want my GitHub Action file to be included as well, such that if I modify my test file, I'm going to execute those tests. I'll do something similar for each of my other services. And then I'm also going to add another key for my migrations. While we don't have any tests to execute for the migrations currently, we will want to build these, and I'm going to use the same approach with filtering for our build workflow. Here, I can create an anchor and call this API Golang and reference it in my migrator section. Effectively, these two will now be identical. Whenever any file changes matching these, both the API Golang and the API Golang migrator will be detected as having changed. I just noted these squiggles. This could either be GitHub_token, or we could have done GitHub.token. Either of those are valid. I like using this to make it very clear that this is indeed a secret value. To get the output of this step from this job to pass it down to the next job, I do need to use the output key here. I'll name the output services. And now I need to reference the set of steps for my ID specifically, the set of outputs from that step, and the output name is changes. That comes from the third-party action. We can look at its action.yaml to see it. Open our action.yaml, look at our outputs. The output is changes, and it's going to be a JSON array with the names of all the filters matching of any change files. Because we want the filter job to run first, we'll add a needs key and specify filter. And then we'll need to figure out how to take that changes JSON array and populate our matrix from it. Let's go ahead and make sure this runs first. Now it's saying our file did not exist. Let's see. So as you can see, I'm trying to filter based on files in my repository, but I didn't actually check out the code first. I need to check out the code, which will use the same approach as down below. And let's try it again. Okay, it's telling me that I either have to explicitly set the base or I need a default branch specified in my event payload. When actually being triggered from a pull request, etc., it's going to have this default branch included in the metadata associated with that triggering event. But here, we can add our own event JSON file and pass that via act to specify it accordingly. So I'll add a new file here in my test subdirectory under workflows. This will be event.json containing repository default branch as main. And then I need to pass that when I make my act call. So in this task target, I can add a -e, pass it my current working directory because the event JSON lives here, and then the file name. Now, if you remember, this action did take in a GitHub token, so I want to define that as well. The way that I can do that is to pass a secret with -s, GitHub token equals, and I'll define this in a second, as an environment variable up here. Right, so this is going to run the GitHub auth token command, which will, based on my logged in session of the GitHub CLI, generate a token, which is then passed into my act command. I will go ahead and, when I'm done recording, revoke access from the GitHub CLI, which should wipe the permissions for any of these tokens that are shown on screen. And now let's see if by adding that event.json file with the default branch included in the metadata, as well as passing this GitHub token, if we'll be able to run successfully. That action performed some git commands, compared the current state of our branch against main, found all the files which were modified, and determined that all of the services defined within my file filter YAML were changed. And so the output of that step is now this list containing each of my services. At this point, I can now modify my matrix strategy to use that output and dynamically execute these jobs based on my filters. This is going to use the from JSON function, and we're going to take an input to that, the needs array, specifically our filter job within it, the outputs, and we called the output services. Now if I run this, we should see the filter job run first, generate the set of services containing all of my services I had before, and run all 4 jobs in parallel. You can see I've got 4 different prefixes there. One's going to be my Go API, one's my Node API, my React client, and my Python load generator. And it looks like all 4 ran and succeeded. Now the main thing that we need to do is, rather than use a workflow dispatch, let's modify this to run on pushes to main, as well as pull requests against main. So I'll start by adding push, filtering down to the main branch. We also want to filter to only run to changes to that services subdirectory, or changes to this file. For PRs, simply specifying the pull request key will run this for any pull request, but because we have that filtering job, if the pull request doesn't touch anything that is relevant, it will skip the heavy test job and only run that very short filter job. And so we now have a workflow which dynamically determines which of our services have changed, and based on that, installs the necessary toolchains, sets up caching appropriately, and runs our tests. Let's go ahead and check this into our branch. We are going to make a few more tweaks to this as we move forward. For example, we're going to pull some of these setup tasks into a composite action that can be reused across workflows. And we're also going to modify it slightly when we add branch protections to our pull requests to prevent merging to main if tests haven't run. There's some quirks around how those are defined and conditional jobs that we need to handle, but we'll come back to that when we get to it. Now, if we go to our Capstone repo and create a pull request based on my branch, we should see that kick off the test workflow. The upstream filtering job ran. It detected that all of the services had changed and kicked off 5 copies of that test job with the matrix strategy. If we click into one of these, this API Golang migrator service doesn't require Node, Go, or Python. It does require task. When we run the test, we see in this case, there are no tests, but we have a command that just echoes no op, no test for the service yet, so that it can adhere to the same interface as the rest of these services. If we click into Node, for example, we'll see pretty much the same thing, except the setup node environment is executed. And when we click into the tests, it actually ran the tests. The next major workflow that I want to author is this build push workflow. This is going to build our container images and push them to Docker Hub. It's going to be a bit similar in that we're going to want to perform a filtering step to determine which services need to be built. Then we're going to build the images and push them to Docker Hub. In terms of the conventions that I used here, each of our services is going to have a Docker file within it. So you can see the Golang one here. You can see the Node.js one here. They'll also have tasks for building a container image, as well as building a multi-architecture image with buildx. And finally, they import this utils task file, which has targets for generating appropriate versions using git describe to leverage the latest release tags within the repo and how many commits away you are from that. So for our production images, we're going to end up with a tag like x.y.z. However, in our other environments, when we build an image, it will get tagged with the latest Semver version that it can find, followed by the number of commits that have happened since that release, and lastly, the commit hash of the build. This gives you at a glance of how far away you are from the production release and the ability to look up the current commit. Each service task file also specifies the container image repo that we'll push to. For example, this is the Docker Hub repo for the Node API, while this is the Docker Hub repo for the Golang API. With this CI API defined, we can now build out our workflow. I'll navigate to my placeholder, and like with our test workflow, let's start by getting it working for a single service. Let's name the job build, push, container images. We'll run on Ubuntu 24.04 and define the steps required. First, we want to check out the code. Let's copy that step from here. In this case, we do need to make one modification. Because I'm using git describe, which uses git tags, I want to use the fetch depth 0 option. So I'll do with fetch depth 0. And this ensures that the git tags and the full history of the repo is checked out and not just the latest commit. This will allow git describe to work properly. Next, I want to make sure task is installed, just like in my other workflow. For now, I'll just copy this step. Eventually, I'm going to move this out into a composite action that can be shared between the two. At this point, I want to authenticate to Docker Hub. On the marketplace, Docker provides this official Docker login action where we need to pass it a username and token. My usage is going to look similar to this, except I'm pinning to the commit hash. Now, in order to do this, we need a username. These are going to be set within the repo. So I'll go and set a Docker Hub username in the variable section and a Docker Hub token in the secret section. Under my Capstone repo, settings, secrets and variables, actions. Under variables, I have Docker Hub username as Sid Palace, and under secrets, I have this Docker Hub token. To generate that, I went to hub.docker.com, signed in, navigated to account settings. Under personal access tokens, I generated this Capstone repo token with read-write access and copied the value that was produced into this secret. At this point, let's go ahead and set up Act to be able to run this locally. I'll create a build push directory. Copy my task file from the test directory. At first, let's create an empty event.json. Eventually we'll use this, but for now we'll leave it empty. And update the workflow it references. Navigating to that directory, if I run trigger workflow, we see that it ran, but the auth to Docker Hub failed because we weren't properly authenticated. In this case, when I'm testing, I generally am not going to want to actually push those container images. So I'm going to add a conditional to my Docker auth step and configure my workflow so that if I'm running it locally, it will skip that. We can do this by specifying a conditional that says only run this step if the act environment variable is not set to true. Now when we run this again, it skips that step and completes successfully. Now by doing this, we are not testing it as part of act, and it's something that we're going to have to rely on testing remotely. However, because it's quite a simple configuration, I'm not too worried about that. There's two additional GitHub actions that I need to set up here. The first is going to be to set up QEMU, and that's to allow us to build multi-architecture images, even though we're running this on a single runner. Eventually, we'll move this to use Namespace's remote builders, and we can eliminate this step. But for now, it's useful to have. The one that I'll use is from Docker. We don't need to provide any inputs. We just need to specify the version we want to use. And then we want to set up BuildX, which is the Docker build tool that we use to build multi-architecture images. Again, we have an official action from Docker. It doesn't require any inputs. My usage will be like this, but I'll pin it to the commit hash. Let's run it once more. We see the job succeeded. Now we need to generate the image tag that we'd like to use when building the image. For this, we'll be able to use those tasks that I highlighted earlier, but we do want to do a little bit of logic around whether we're building for production or staging, etc. The way I'm going to design this is that for pushes to main, we'll consider that a deployed to staging, and production will be deployed on specific release tags following a convention for each service. I'm going to start by just using a placeholder. I'll just hard code a version. I'll hard code an image tag and write both of those to the GitHub output. Because I'm going to reference this in the next step, I do need an ID here. I'll call it image tag. And let's add a to-do, generate the actual version / tag. From here, we can actually build our image. For this, we can use the official Docker build and push action. There's a whole bunch of different inputs we can provide to this. We're only going to need a handful of them. We'll use version 6.18. First, we're going to specify the context. And the context is going to vary for each service. But because we're establishing our baseline for just getting it working with one, let's use the Node.js image. So this will be services / node / API node. The push input, we can actually use that act environment variable again. If we're not running an act, go ahead and push. If so, skip it. For our tags, this is where we're going to use the image tag from the previous step. And we can say steps.image tag outputs image tag. This was tags plural. We can specify platforms. In this case, while we do have QEMU set up, so we could build it across multiple architectures, in order to keep it as fast as possible, let's only specify the architecture of the runner itself. So do Linux / AMD 64. And then we can use the caching options to say cache from of type equals GitHub Actions. So this is going to leverage the GitHub Actions cache to store and retrieve layers. And then cache 2 will similarly say type equals GitHub Actions and mode equals max. Now, when we shift to using Namespace's remote builders, we can eliminate these caches, but for now, it can be useful. Let's try running it. Looks like it's actually building our container image, and the job succeeded. Awesome. So at this point, we have a workflow that can execute end-to-end. It configures Docker and uses the convention of having a Docker file within each service to build out that service. Now let's perform a similar approach to what we did with test to use a matrix strategy to build all our services in this fashion. I can copy what we did for test. We're going to have that upstream filter job. Then we'll add our matrix strategy and modify our context to use the matrix.service. Now if I run this again, first I noticed that we are missing our needs key here to specify that the filter job must be upstream. But we also get that same error as before where our default branch was not specified. Let's copy the event.json from the test work file to ensure that it's defined. Now our filter job output all the different services, and our build push job is going off and setting up and building all those container images. Looks like it's done setting up Docker, and it's actually building all those containers in parallel across the different jobs. And so just like that, all 5 of our container images were built. Because we're running an act, we did not push them, but our workflow appears to be working as expected. So what else do we need to do here? We still need to get our version tags working properly. This is going to require some nuance around deciding whether we're building for a staging environment or a production environment, and then calling into the appropriate tasks. We also copy-pasted this install task step across our two workflows. I was thinking it could be useful to abstract this out into a shared composite action, along with some of the other toolchain dependency installation stuff that we saw in our test workflow. Now, the convention that I like to use here is to put actions within a .github/action directory. I'll then create a directory with the name of the action I want to use. And within that, I need an action.yaml. I'm going to name my action setup dependencies, and I'll describe it as setup tools and dependencies. Now, eventually we're going to need inputs, but for now I'll skip it. Then I can specify the runs key using composite. And now I can specify the steps that should live within it. Let's start by just adding that task step directly from our other workflow. Eventually we can pull out the version as an input, but for now, let's just leave it as is. Now within my build push workflow, instead of calling out to that third-party action directly, I can replace this with a reference to my composite action. Let's see if that still works. I'll comment out the bottom of this and hard code my service matrix so I only run one copy of it. But now, if I trigger this, despite moving the task install step into the composite action, it still gets executed here. Let's make this a little more versatile by allowing us to specify the version that we want. So as an input, we might take as a Boolean to install task or not. So if this is true, we're going to install task. We'll default it to true. And then we can also specify a version. And we were installing 3.44.1. Also, this needs to be a string. Input types have to be string, so I'm changing this from a Boolean to a string here by adding quotes. Now within our step here, we can make it conditional. If inputs.install task equals true. This is a quirk of the fact that you can't pass a Boolean as an input. That's why we have to check if install task matches the string true directly. And then we can also template our version here as well as here. Let's run it again. We can see we got our version of task installed. And if we wanted a different version, we could do so by modifying our usage of this composite action to say with task version, let's say v3.44.0. And so we get that other version of task installed. For now, I'll just accept the defaults. Eventually, if there were more workflows that depended on having the Node.js or the Go or the Python toolchains installed and configured, we could move those to the setup dependencies composite action as well, and share all of that logic such that each workflow would call this setup dependencies composite action, and it would handle all of that toolchain setup for us. Okay, now that we're avoiding that copy paste across workflows, let's go ahead and work on removing those hard-coded version tags. Now, I don't need to actually build the image here to test this. I just want to make sure that my version tags are looking good. In order to do that, I'll actually just echo these to terminal. We don't need to write them to the output. So now if I run this, we see those were echoed out. Also, if we're not actually building the image, we can skip our setup of these dependencies. I'll add them back once I'm done getting this working. There we go. Okay, now we're able to very quickly run our workflow and see that these are coming out properly. There's a few factors that determine what we want our image tag to be, one of which is whether it's the production environment or a non-production environment. And so I'm actually going to add an environment variable here. Environment. We'll start with the production, hard-coded. Eventually this will be dynamic. And we also need to know which service we are running against. In this case, we can get that from our matrix. Now finally, because we want to execute the task file from the same directory as the service, we'll set our working directory equal to matrix.service as well. Now for version, instead of this hard-coded value, we can execute this task. So task utils generate version, passing it the name of our service. And for the image tag, it will be very similar, except it'll be generate version tag. These are coming from that imported utils task file. If I look at it, it's going to use git describe, finding a git tag associated with my service, adding in a prefix and echoing it out. And then for the version tag, we're just appending the image repo to the front of it. So if we go ahead and run this, let's see what we get out. So for my version, I got version 1.0.9. There have been 47 commits to the repo since then. My current Git hash starts with 1A8F7. For the image tag, it pulled the image repo out of my Node API task file and appended that to the front. And so now this is a valid container image tag that I could use to tag my image and push it to Docker Hub. If I now add these steps back and these steps back, I can make my matrix dynamic again. And with that, I should now be building all 5 of my container images with appropriate tags. However, this environment of production is still hard-coded. Now I have a variant of this task called generate extended version tag, which will produce these tags where that center number of commits is left padded with zeros. And the reason for this is that I want my versions to sort correctly alphabetically. If you don't left pad this, then let's say 11 commits comes before 3 commits because it starts with that 1, if you're sorting alphabetically. This is useful in a variety of other tools. And so as long as we don't go more than 10,000 commits between releases, this format should be good to go. To handle this, I want to add a conditional here that basically says if it is production, we'll use this one. However, otherwise, we want to use the extended one. So this will be extended. Let's just test this as staging, for example. We'll comment these out again just to validate. And now, rather than just having 47 here, we've got 0047, which is what we want. So how can we determine which environment we're deploying to? Also, if we're building based on a release tag, our standard paths filtering approach is not going to work. Instead, we want to use the tag itself to determine which service it is associated with. So in our filtering job, if we're pushing to the main branch, we want to use the standard approach that we've seen. If we're pushing to a tag, we want to extract the service name from that tag and set that as our service for the matrix. Let's call this step set output. We'll ID set output. And for this, we're going to run, and we'll have a little inline bash to determine exactly that. We'll start by saying if the GitHub ref is of type tag, then our tags are going to look like service, node, API, at, and then a version. We want to extract the tag using the GitHub ref name environment variable. We can then extract the service name from that tag using a bash expansion, extracting everything before the @ sign. And so if this is our tag, then service will be this. And in this case, because it's coming from a tag, we want to use our production variant. So we can say echo services equals, we need to escape our quotes here. Here, our services matrix is going to be a single service based on the one we extracted from our tag. We want that into GitHub output. And we want to echo environment production. The other case is generally going to be our push to main. For that, we do want to use the output of our filter. So we'll output the changes from that step into our GitHub output. And we want to specify that it's going to the staging environment. Now end our conditional. At this point, if we're coming from a tag, we'll use this approach. If we're coming from a push to main, we'll use this approach. Now, one more thing that is useful is to be able to manually execute this workflow for a particular service and version. In order to do that, I'm going to add one more conditional. So this will be else if. And in this case, I want to check if the triggering event was a workflow dispatch. So this allows me to trigger it manually. If it was, I'm going to add an input here of service and version. For description, this is the service to build. We can make this of type choice. So this will actually give us a dropdown in the GitHub user interface, make it required, and specify the options. In this case, we want our options to be the services as defined. For version, we can specify that it's the version to use for tagging images. In this case, we can specify an explicit version, or we can let it fall back to the git describe. I can now set my services matrix here using that input. And let's say if we're running this workflow manually, we want it to be the development environment. So now instead of taking it from my filter step, I'm going to take this from my set output step. I also want to take the environment from that step. And I named this services instead of changes as defined here. So now let's see what happens if I run it. Okay, the error that I got is that my task doesn't exist. I think what happened is because I didn't specify an inputs.service, this ended up empty, and it tried to run against that empty path, in which case there was no task file, and there was therefore no task defined. I can modify my event.json to say inputs, service, and pass it the Node API. And now it worked as expected. This does bring up one additional bug though. If the path filter outputs an empty array, it seems that the downstream job still tries to run, but just with an empty string as the service name. Let's add a conditional to that step to handle that case. I found this issue on the repo of someone who ran into a similar problem where when you have an empty array, you hit some issues. And the author of the action provides this as one potential option for handling this. This looks good. I think I named my upstream job filter instead of changes, so I can modify that. But otherwise, it's saying only run this job if it's not equal to an empty matrix and it's not equal to an empty string. So I can add my conditional to this job, and that should handle the case where no services have changed. I actually need this in my test workflow as well, so I may as well add it. And now we should be in pretty good shape. One piece of logic I haven't really validated is this bash script to extract the tag from the git tag. If I wanted to validate that, what I could do is add a separate event.json. In this one, instead of using a workflow dispatch type, I'll make this a push tag event. And within this event, I'm going to specify a ref and a ref type of tag. And this corresponds to an actual release in my repo that I want to test against. I now need to add a task to my task file. In this case, I'll copy this. We'll call this trigger workflow tag. We'll pass it the name of our new event. This will be a push event. And we want to make one additional tweak, and that is to add the no skip checkout flag. And what this does is rather than mounting my local code into the containers as it's testing, it's going to do the checkout based on the ref in my event JSON. Let's give it a shot. So I'll do trigger workflow tag. It's saying there's no workflows to run, and that is because my workflow currently only has a workflow dispatch trigger. Let's add triggers for pushing to main and pushing to tags that match our desired convention. So we can do push, branches, main, paths, services, ***. So this will build images when we push to main with a change to at least one of our services. And then we also want to trigger on pushes to tags that match a particular convention. So in our case, our convention is going to be any tag that has some string followed by the @ sign, followed by a semantic version. So number, dot, number, dot, number. Now I can attempt to rerun it. It successfully found that trigger. It failed on that same thing we've been hitting before with the Node 24 version. This is because the checkout action also was upgraded recently. To get around this, I can use a slightly older version of the checkout action, which uses Node 20. Again, this would not be an issue when running on actual GitHub Action runners. It's just a limitation of my current version of Act. I'll do it here as well. The reason I didn't hit this before is by default, Act is going to skip the checkout step and mount our local code into the container. But here, we want to check out the code from GitHub associated with this tag. And so it hit the issue. If I run it again, looks like we successfully checked out our code. Seems like we still needed this default branch to be included in our tag event. So let's try once more. Scrolling down, it looks like it successfully set our output as the production environment and our service as services go API Golang. So that appears correct. Now our failure is that we are no longer successfully installing task. Because this API Golang tag is referring to an older version, that composite action doesn't exist. So to get around this, let's go back to how we had it before, where we were just installing tasks directly to avoid the need for that composite action to exist. So I'll just copy it from here. We'll temporarily remove this and instead install it directly and try it once more. So that's the benefit of skipping the checkout. You automatically can utilize local changes without needing them to exist remotely. However, for testing certain things like this, we want to use an actual git tag. Okay, interesting. So it successfully generated a version based on the tag that we gave it. However, in this case, for a production image, I would want this to just be 1.0.1 without the extended information. Let's see where my bug is. We've got environment production. So my environment was still hard-coded to staging here, which is why I got that extended git tag. Instead, I can do needs.filter.outputs.environment, which I set up above here. And now, If I rerun it, let's see if I get just the 1.0.1 as my version. And there we go. Now it appropriately identified that because I'm in production, I want to use the shorter version rather than the extended version, and we see that reflected here. Now, if you'll remember, I also passed a version in via the workflow dispatch, and let's go ahead and use that if it's defined. So I'll make this an else if, make this an if. We can extract the input version here, and that'll either be, and say, if it's a workflow dispatch, go ahead and pull it out. Otherwise, set it to an empty string in our script. If the input version exists, we'll go ahead and use it by storing it in the version variable and then passing that into another task target we have called manual version tag, which rather than using git describe is going to take that version specified and append it onto the repo defined within the task files. To validate that, I can go back to my event here. Let's call it a workflow dispatch event. We can add version foo var baz, update this task name to workflow dispatch, reference the new name of the action. And now, because we have a version specified in that workflow dispatch, we should hit that branch of the conditional, use it, and tag our image accordingly. And so here, you can see the version is foobar baz, and the image tag ended up with my node API as the repo and the foobar baz as the version. So now that's working as expected. At this point, we can go ahead and push it to our branch. And now, because we don't have a trigger for pull requests, and we're only triggering on pushes to the main branch, we wouldn't expect any runs of this workflow to run. But because we've used act to validate the different conditions, I have relatively high confidence that it's going to behave as expected. We'll see this in action once we get the rest of our workflows in place, and we actually start to merge some PRs, modifying services within the repo. I can go ahead and uncomment the steps that I have commented that were just there for testing purposes. Push that to GitHub. Okay, with our test workflow and our build push workflow in good shape, the next major workflow that we want to build out is going to be that one in the bottom right, the update GitOps manifest workflow. So this is going to be kicked off at the end of our build workflow. It's going to take the version of the images that are built and update the corresponding references within our Git repository for the Kubernetes manifests that would deploy these applications out. So we're going to kick it off from that build push workflow. We're going to check out the code base containing those configurations, update them, and then commit those back to the repo. Now, I could have put this logic as a separate job within my build push workflow. However, I think separating it out makes it a little cleaner and easier to read. Also, having them decoupled allows me to run and test one without impacting the other. I have this placeholder workflow here that will update to handle this process. The first thing we're going to need to do is to check out the code. I'll use the same version I'm using in my other workflows. As inputs to this workflow, I'm going to take both the service, the version, and the environment. All three of those are going to be required. We'll give them a description. We'll specify their type. In this case, I'm going to use choice. This will allow me to have a specified set of options to choose from to ensure I don't accidentally input an incorrect service. And these are going to be all the choices that are available. I forgot the input key. Version will be of type string. For environment, let's have 3 choices, let's say. Development, staging, or production. I'm going to have a single job called update manifest. Most of the heavy lifting here for actually modifying the state of the repo and committing that back is going to be handled with tasks. So once again, I'll need to install my setup dependencies composite action. Now I can copy that from my build push action, copy a reference to my composite action here. We configured that to by default install task at the appropriate version, so we don't need any inputs. Let me show you within my task file the script that's actually going to do this updating. It's going to be under utils, task file, update image tags. And so what this is going to do is going to recursively go through my repo and find any file containing a specific comment within that file, replace the version associated with that comment. Essentially, I provided a tag, a comment to look for, and a starting path within my repo as the entry where it's going to recursively search from. I also have a set of specified excluded files such that this action doesn't modify this task file or somewhere else if I had a README where one of these identifier comments was defined. You can see I'm just searching for all YAML files from that starting path, grepping for my identifier comment, and then looping through each of those and updating them. There was a weird quirk around how the default version of sed on Mac OS and Linux behaved. Because I'm using DevBox and installing sed there, it should use the new version and behave appropriately. For a particular service, I'm formatting my identifier comment as the environment _ and then the service release tag. Let me show you what this looks like. Under the deploy subdirectory, under Kubernetes and Clucuttle, I can click into the services and find one of my manifests. So this is the deployment YAML file that will handle the deployment of my Node API. As you can see under the image tag, we're using this template for API node.version. If we look in the config directory, there's a production.yaml and a staging.yaml. The staging.yaml has the version we want deployed to staging with that identifier comment. So again, it's environment _ and then path to service. In the production environment, it looks similar. However, we're using the production prefix instead. So when we run this update image tag, passing it an appropriate environment and service release tag, it's going to recursively find all of those associated references and update them accordingly. So I can have a step, update manifests. We need to set the working directory to call this from within the appropriate service. And then we're going to call that task that I just showed, and we're going to pass it the new tag as the version that's being input here, and the environment from the inputs as well. As a test, I'm just going to run git diff to see what this command modified. Now I want to be able to run this, so I need to create my act command. I'll go ahead and create a directory with a task file referencing this workflow. It's using the workflow dispatch. I should no longer need this because I'm not using that filter step, but I do want inputs, service. Let's use node as our example. Services / node / API node. Version, we'll just set it to foobar baz, and environment, we'll test with staging. Now if I trigger my workflow, it's not properly picking up the version of sed to use. Let's see why that is. So in my task file, it's trying to pull in this variable to use as the sed binary. And so previously, I had been dynamically detecting whether I had the macOS version of sed or the new version of sed. Once I added that to DevBox, I removed that. And so this is no longer necessary here. And I can just call sed directly. If I run it again, we can see this time it did run successfully, but it's showing us a diff associated with our local updates and all of the changes we haven't committed yet. Let me go ahead and commit these to my branch and run it once more. All right, now the only diff we see is that it found my version within that staging configuration file for the Node API and replaced the current version with foobar baz that I input. This is exactly what I wanted. Let's try it again and instead make my input have the production environment. I'll also modify this to be Bing. So now we want it to find the production config for the Node API and replace the current version with foobar baz Bing. First, we see the diff of our event.json. We don't actually care about that. Because git diff is an interactive command, it's not actually logging that all the way out. Let's modify our test command to add the no pager option to our diff. This should spit out the full diff to the terminal. And so we see both the change to our event.json that's expected, but also it identified that production.yaml based on the corresponding comment and replaced this version with the new version specified. So it appears to be behaving as expected. However, this change only exists in the workflow at runtime, and now we need to commit it back to the main branch. When I first attempted this, I used this third-party action, git auto commit. It takes whatever modifications you've made during your workflow and commits those back to a specified branch. This worked fine when I was testing it. However, because I can potentially have many of these workflow deploy GitOps update workflows running at once, I ran into the case where I would check out the code, make my changes, and another workflow independently would commit in the meantime. There's a couple of ways I can handle this. One is I can modify the concurrency settings for my workflow to ensure that they all run in serial. This would work. However, it would be slow and not necessarily ideal. What I did instead was move some of this logic into my utility task file, into this commit push action. So here I'm taking in a commit message, a branch, a number of retries, some amount of delay, and then some amount of jitter so we're not retrying at the exact same time, this will take the changes that are made in my workflow, attempt to commit them. If they fail because of a conflict or another update to the main branch, it will pull the latest from main, attempt to reconcile those, and then attempt to recommit again. Now by default, I'm going to retry up to 5 times with exponential backoff in between. By default, I'm going to have a commit message structured like this: chore, automated update, skip CI. However, we can generate a commit message that contains information about which service is being updated. Let's go ahead and do that now. So before I update here, because I'm going to use an output from this step, I want to give it an ID. And essentially, I'm going to take the information provided as inputs, the service, the version, the environment, and write the corresponding commit message. So I want to say chore, update, environment, comma service, comma version, skip CI. Now the skip CI tag will tell GitHub not to run any associated workflows on those commits. Then I want to store that to the output. And now we can consume that down below when we actually perform our update. Because this is actually modifying the state of the repo, I'm not going to run this within act. So I'll add my conditional to avoid running this locally. This is the type of thing that's quite hard to test locally because you're actually modifying the remote state of the Git repo. I need this to run from within my service directory. And the actual command I want to run is going to be a task command coming from that utils task file, and it's going to run git commit push. And we do need to provide some inputs. So the commit message is going to equal the output from that other step, the branch that we want to commit back to. So now we have the ability to generate the necessary modifications to our GitOps manifest, as well as an appropriate commit message, and then commit those back to the main branch. One thing I mentioned earlier is controlling the concurrency of this. So it's likely that this workflow is going to have lots of different instances for different services that are being updated in parallel. So let's add a concurrency key with a group and a cancel in progress. We can use this so that only one of these workflows is running per service per environment. To do that, we want to define the group that includes the workflow, the environment, and the service in the key. This way, let's say we had 2 updates to staging happen back to back for the same service. We'll run the first workflow to its entirety, deploy that version. Once that is finished, we'll deploy the second version. This helps to avoid 2 updates trying to be applied to the exact same configuration file at once. Let's run it once more. Okay, and with that, we have this workflow working as expected. However, we still need to trigger this from our build workflow. So let's jump back to build push. We can add another step to our build push job. This will be trigger deploy. Again, we don't want to actually trigger the deploy when running within act, so we can add our conditional. Here we need to pass it a GitHub token because we're going to make API calls against the GitHub API. And the GitHub CLI uses this environment variable to load in the token. In order for us to have permissions for this token to make commits back to main, we need to update our job permissions. So under the build push container image job, we can add permissions key and give it the ability to not only read the contents of the repo, but also write to our actions. Now we just need to issue a GitHub CLI command to trigger that workflow. That's going to be GitHub workflow, pass it the file where the workflow lives, along with the inputs of our service, our version, and our environment. When this workflow ends, each of those matrix jobs is going to trigger a copy of that other workflow to update the GitOps manifests. At this point, we have our 3 primary workflows built out. We can make modifications to our code base, test them on a pull request. When we merge that and push it to main, it will build our images and deploy those out to a staging environment. We could also manually tag a release for any of our services by pushing a git tag with the appropriate format. However, there's a couple of additional workflows that I want to implement to make our lives a little nicer. First, we can automate that release process using a tool from Google called Release Please. It'll look at a specific format of our commit messages to determine the next appropriate version and automatically generate pull requests and tags to release our code to production. Also, to keep our repo tidy, I'm going to use the stale action from GitHub to look at any issues and pull requests that haven't been touched or updated in some period of time, mark those as stale and close them. And then finally, to give us better visibility into the execution timing of our workflows, I'm going to export the timing data from our test and build push workflows into Honeycomb, where we can track and observe them over time. All 3 of these workflows are pretty much just leveraging a single third-party action to handle the functionality. And so implementing them is mostly an exercise of reading the documentation and applying them to craft the correct configuration for your repo. Rather than build them out in real time, I'll showcase the action documentation and how I've configured them to run within our project. Let me go ahead and check out the main branch. And we'll pull up the release please workflow. Here, the primary execution is going to be on every push to the main branch. As I mentioned, we're going to have a single job with a single step. It's going to run this third-party action. And then we need to configure a few things. First, we're passing in a token. Now, I could have used the auto-generated token with the appropriate permissions here. However, there's a nuance with GitHub Actions. Any workflow runs triggered from within GitHub Actions using that token will not run associated workflows. One way to get around that is to use a personal access token instead. In this way, the PRs generated by this workflow will behave as though they were created by whichever user this personal access token is associated with. Next, I'm passing it the path to a config file and manifest file. I'll pull those up in a second, but this is how we actually configure the tool to behave how we want and tell it about our various services. Also, I'm targeting the main branch as the branch to create PRs against. The manifest file is located at .github/utils/release-please-manifest, and it contains a listing of all our services and the current version. Now, there is some documentation in the release please documentation talking about how to bootstrap this. You can actually install release please on your system and run it locally, passing in a GitHub token to bootstrap the various files. In my case, I just crafted this manifest file by hand and input the correct starting version for each of my different services. The release please config file is where most of the important configuration lives. The sections that we want to look at here is this packages object. So here we have one entry for each of our different packages. This first part is a path within the repo to that package. And then we have a component name and then a release type. The release type determines what modifications release please is going to make, whether it's updating your package.json file or a go.mod file. And there's a number of different release types available within the documentation. You can see here we're using Node, Python, and Go. Line 4 is important because we have this mono repo with multiple services in it. We'll include the component name in our git tag so that we don't have conflicts between tagging different services. I'm opting not to prefix with the letter V. You can choose to either have v prefix, so v x.y.z, or just x.y.z in your tag. And then down here at the bottom, I'm using a plugin called linked versions to tie together my Go API with the migrator code. So if either of these two are bumped, those versions will move in lockstep and be released in tandem. Now, one final change that I made here is this changelog sections block. So by default, release please is going to look for commit messages that start with the strings fix or feat. So if we look here under conventional commits, this is the format that it's using. So you'll have a message that starts with either fix : or feat : and then the rest of your message. So here, this would be for a new feature, allow provided config object to extend other configs. You also can specify that something is a breaking change by adding it here in the body of your commit message, or you can append an exclamation point after the type. If you do either of these things, it will bump the major version of your semantic version with the next release. Now, by default, release please would only use these first two types. However, when using this in the past, I found it convenient to also include chore and revert when determining the appropriate messages. And so with that in place, let's go ahead and take a look at how this works. Now, I have a few pull requests here that I have added throughout filming this to make modifications, one of which was when we added the no pager option for the git diff command. Let's go in here. I made this change. I'm following my conventional commit format, and I'll go ahead and squash this and merge it. Now, because this is a new commit to the main branch, we should see a release please action run. It's going to check out our code, look at all of the different commits that have happened since our last release, parsing them for that conventional commit format to determine the appropriate services to update and what version to use, before creating or updating a corresponding pull request. So if I go in here and look at this pull request that was created a while back, I can see it's detected all of these different changes since my last release. Within the PR description, we can see what they are and which commits they came from. So in this case, I added a dependency install step. I added some example tests as new features for my Node API. And you'll notice the version for my Go API and my migrator code are identical because I'm using that linked version plugin. It also includes this auto release pending label on my PR. Once I merge this, that will trigger another execution of release main, where rather than create a PR, it's going to go off and actually create these tags. Those tags will trigger runs of my build push workflow for the various services, which in turn will kick off my GitOps manifest workflow. Let's see that happen. So I've merged my release PR. It kicked off a few workflows from that main branch. But now when release please runs, it actually tags our services. So we see our Go API is now tagged at 1.3.0. It also creates a GitHub release. We can see under the GitHub releases page. This was just released a minute ago, as well as this. Going back to our actions, we look at our build push container images workflow. Each of our services had a build, and when they complete, they trigger via that workflow dispatch the update GitOps manifest workflow. Okay, we see some of them are succeeding, some of them are failing. Let's check out why one of these might be failing. So this was that issue we had with sed that we patched while recording. I haven't merged this workflow yet, so let's go ahead and do that. And you'll notice, even though we ran our release please workflow, we didn't get a new release PR. That's because that PR didn't modify anything that corresponded to our services. Let's make a quick PR that touches one of these services and see it play out. I'll pull the latest on main. We'll make some trivial change to one of our services. Let's do the Go API. I'll just remove a new line here. We'll create a branch to commit that to. Commit it, push it, create a PR from that branch, merge our pull request, check the release please action. We can see it created a new PR, number 40. If we go to pull requests and look at it, you'll see it detected our change to our Go API, including that commit we just made. Let's go ahead and merge this to release that change. It's created a new release for both our Golang migrator code as well as our Golang API code. Now that those two have completed, it should have triggered 2 runs of our update GitOps manifest workflow. Clicking into it, we can see it's deploying against our production environment. If we look at our git diff step, it correctly identified that it should update the configuration for our production environment with the appropriate new tag. It then committed that back to Git. Let's look at our repo. We can see the latest commit to the repo is from that GitHub Actions bot, making the desired change. And so now we have this automated approach to producing releases of our different services and tagging them with an appropriate version based on the changes that have been made. Now, the final 2 workflows that I'm going to add are more of just auxiliary workflows that I think are nice to have. The first of which is to use the official GitHub stale action to determine if there are issues and PRs that have not been touched in a while and clean those up. Here's the marketplace page for that. It specifies that you should give it certain permissions, depending on whether you want it to be able to delete branches or just close the corresponding PRs. And I'm going to use this in its most simple format. There's a number of options you can provide. You can tell it how many days you want an issue to be untouched before you mark it as stale. I'm going to go with all the defaults here, which will use 60 days before something is stale, and then another 7 days before it actually closes. Because I'm using all the defaults, my usage will look very simple. I'm going to run this daily. I'm giving it permissions to write to both issues and pull requests, which will allow it to add comments and close those if they are stale. I have a single job with a single step using the latest version of that action. Now, I set this up a while ago, so we should have an issue to test the stale bot. I created it July 22nd, and it looks like we haven't waited quite long enough for that default 60 days to pass. Let's go ahead and modify this to shorten our input and say days before stale. We'll just call it 30. Shorten stale length, commit that back. We'll want to merge our PR back to main. And now, rather than wait for that daily run, I do have a workflow dispatch trigger on it, so I can go ahead and run it now. It queried against the GitHub API. It found 1 stale issue because now the issue I just showed is older than that 30-day threshold. Let's see if it added a comment. If I go to my issues to test stalebot, it didn't add a comment. It added a label, stale, and now it will use that label. And after 7 days, if nobody has touched this issue, it will go ahead and close it. So a workflow like this is super easy to set up and helps to keep your repo tidy. And the final workflow that I'm going to show is this export timing data workflow. I showed earlier in the course some of the results of this data going into Honeycomb and being able to break down at a very granular level and track over time the different execution timing of our workflows. But I'll just show how I've configured this. The action that I'm using is this OpenTelemetry CI/CD action. It actually exports it using an OpenTelemetry format, so that can go into a variety of platforms, including Axiom, New Relic, Honeycomb. I like Honeycomb, so that's the one I've used. You list out the set of workflows that you want to run against. This is the name of the workflow as defined in the workflow file. And then I'm specifying that I want to execute this when these workflows complete. I now have a single job with a single step using that third-party action. I've pinned it to the latest version. This will be dependent on whichever provider you're using. In this case, I'm setting it to the Honeycomb API. I've then generated an API key from the Honeycomb platform. So if you go here to your Honeycomb account and you go under Manage Data, Send Data, you'll see this API key here. You could click it, copy, or view. And now the particular format that this is looking for is to specify it within a secret under the X Honeycomb team OTLP header. So I created a GitHub secret called Honeycomb OTLP headers. I then passed it this value, including the API key that I grabbed from the Honeycomb platform. I then also extracted the run ID from the triggering event so that it knows to go off and find the associated timing data from that GitHub event. And so each time any of these workflows run, we'll get a copy of this workflow, which will grab the associated timing data, format it appropriately using the OpenTelemetry standard, and export that to Honeycomb. So for all those workflows that I've just been running, if we go under Actions, over the last 15 minutes, I've got a whole bunch of copies of this. They only take about 10 seconds to complete. They grab the associated timing data from the GitHub API and ship that off to Honeycomb. Now if I go to Honeycomb and go home in the last 30 minutes, you can see I've sent a whole bunch of spans associated with these different builds. I can click in to view a particular trace and see the breakdown to the step level of how long they took and the sequence in which they executed. I'll leave it as an exercise to the viewer to go off and build dashboards on this data to do things like track this over time, set up alarms if things get slower than expected, etc. And so with that, we've got a pretty robust DevOps system built out using GitHub Actions that allows us to do both continuous integration as well as continuous deployment via GitOps, and some niceness around developer experience associated with the repo and understanding the execution of our actions over time. Now, throughout the duration of the course, you've heard me talk about the sponsor, Namespace. Let's spend the last few minutes showcasing what it takes to migrate an entire project like this over to using Namespace for the runners, for caching, and for remote container builds. As you can see from just a handful of lines on this slide, it's a relatively painless process where we'll find and replace a bunch of runs-on types, specify some labels to ensure that our caches behave appropriately, and even remove a few setup steps which are no longer necessary. With these changes in place, my runner execution is going to cost about half of what it would on the GitHub hosted runners, and my execution times, from the improved runner performance, the improved caching, and the remote builders, allowing me to build multiple architectures natively, should significantly reduce my execution time. We can start by replacing Ubuntu 24.04 across all of our different workflows. I can search across the whole project for the string, and then I can replace it using one from Namespace. We saw earlier in the course how you can use Namespace profiles to specify the operating system, the machine type, etc. However, rather than manually managing profiles, you can also use labels with this convention, NS Cloud, the operating system, the architecture, and then the shape, meaning how much CPU and memory, to achieve the same thing. So I'm going to replace runs on Ubuntu 24.04 with runs on Namespace Cloud, Ubuntu 24.04, AMD 64, 4 CPU, and 16 gigs of memory. Replace all. And so just like that, I've cut over all of my workflows to run on Namespace Cloud runners. Now that we are running on Namespace Cloud runners, there's a couple of steps in my build push workflow which are no longer needed. Specifically, setting up QEMU and setting up BuildX will be handled for us by the runner. QEMU won't be used at all, since Namespace will execute these builds on separate runners, one AMD 64 and one ARM 64, so that those builds run natively and can execute much faster. And then BuildX will already be configured to point to those remote builders. If you wanted to use the remote container builders from a different runner, instead of running this Docker BuildX setup action, you could run the Namespace Cloud setup action followed by the setup BuildX action to configure BuildX accordingly. Now the final piece that I want to change is to use Namespace cache volumes rather than the GitHub Action cache, Node, Go, and Python dependencies. Once again, you can manage cache volumes with profiles. You can also use labels within the runs on section, and so that's what I'll do now. Within the test workflow, this filter job doesn't need any caching, so we can leave it as is. But we want to establish cache volumes for each of our different services. That way, each of them caches the specific dependencies of that service and don't pollute the other caches. And Namespace doesn't get confused about which files ought to be stored in that cache. The documentation for using this runners label feature is here. We'll append with cache to the end of our machine label. And then we'll add some additional labels here to specify the size of the cache and ensure that each service gets its own. This label will give us a 20 gigabyte cache. This one tells Namespace to only commit new files to the cache from main. This will avoid unnecessary updates or polluting our cache from PRs, which may have different dependencies, and will generally always be pulling a cache volume in sync with the latest version of main. Finally, we want to specify a unique tag for each service such that cache volumes get provisioned for each of them. My first attempt at this was to reference matrix.service, which seems like it should work. However, you can't have forward slashes in this context. And because my services are named after the path within the repo, they have forward slashes in them. Instead, I ended up needing to modify my filter job to include an additional matrix value, replacing those forward slashes with dashes. I add a step here, which uses this JQ command to generate a JSON object with one entry for each service containing the service, as it was specified before with the forward slashes, as well as a new value cache label where we're substituting a forward slash for a double dash. I'm then writing this to the output of this step. Need to also add it as an output of the job from that step, at which point, instead of specifying matrix service here, I can replace this with a matrix include key where I consume that array of services that contains my new key. So before I had services foo/bar baz/bing, and the matrix strategy would run one job for each. I now have include service foo/bar cache label foo/bar baz/bing. And so by passing this object into my include, I'll get one job with these as my inputs for that job. I'll still be able to reference matrix.service exactly as I was before, but I'll also have this cache label available to me, which I can use to create a service unique tag to tell Namespace to create a cache volume for each service independently. However, just because we created a cache volume doesn't mean we're using it quite yet. Now I need to configure for my different services where specifically within the file system Namespace should cache. That's going to depend on the specific runtime or package manager that's being used. For this, Namespace provides a custom action with examples of how to configure it for Go, Yarn, Rust, etc. Or you can specify a set of paths within the file system to cover any case you can think of. For Go, we're first going to disable the GitHub Actions caching by specifying cache false in our setup Go action. Then we'll add a step which only executes if we're installing Go, uses that namespace caching action I just showed, and tells it to use the Go cache. We'll do something similar for Node, where we'll disable the upstream GitHub Actions cache by providing an empty string. We'll copy this, run it when we're installing Node. And because NPM is not one of the default options, we'll use a custom path input. We want home.npm, as well as the node modules directory where our service lives in the codebase. Python will be similar. Once again, adding an empty string here disables the GitHub Action cache. Run it only when we're installing Python. And use the poetry cache. And you may have noticed I was doing this within the setup dependencies composite action. One thing I didn't show in the recording was migrating these language setups into that composite action. Similar to how I moved the setup of task into this composite action, I also moved the setup of Node, Python, and Go in case I ever needed to use them across other workflows. I added Boolean inputs for each of the different languages to decide if I'm installing it or not, and then a path to the service where I can find the relevant pyproject.toml file, go.mod file, etc. Consuming this now looks like before, but I use my service name to determine if I should install and configure each of these runtimes. The process The process of moving these out is almost identical to what we did with task, so I didn't think it was worthwhile to showcase doing that. I just wanted to clarify why you might have seen a slight difference in where this logic lived, but I wanted to handle it in the same place that I was handling the runtime setup. To summarize, we modified our runs on to use namespace-based runners. We configured them to set up independent cache volumes for each service where appropriate, and cache dependencies from each of our specific toolchains. Also leveraged Namespace's remote container build service for faster multi-architecture builds. As you can see, the level of effort we put in for the cost savings and performance increases is well worth the investment. I would urge you to spend just a little bit of time to investigate how moving to Namespace might help your org build and ship software faster. And with that, we've reached the end of the course. Taking a look back, we started by learning about the history and motivation for continuous integration and where GitHub Action falls within the competitive landscape. We built a foundation by learning first about the core features of the platform before moving on to more advanced concepts. We then explored how to use third-party actions as well as author our own, before covering how to author workflows that meet the needs of your software teams. Finally, we brought all of this together into a comprehensive Capstone project, implemented build, test, and deploy workflows for a realistic microservice application. My goal for this course is for it to become the go-to resource for people who want to learn GitHub Actions effectively. If you found value in the course, consider sharing it with your colleagues at work or with your network on social media. If you do so, please tag me. I'm at Sid Palace on Twitter, or you can search Sid Palace on LinkedIn. Thanks again to Namespace for sponsoring the course. And remember, just keep building.